Thanks everybody for joining the Advanced Computer Science Summit for AI in Healthcare for HDR UK. I'm Dave Robertson, and really I'm just the host for this session. We'll try and keep the time because I know people have commitments. We'll try and finish at 3:30. And we'll keep it informal if we can. So a lot of us already know each other a bit through Health Data Research UK. Some of you don't. People are joining from some other organizations, from the Turing Institute, for example. So we'll see how we go. The way we've set it up is a series of talks with a fair bit of a gap for conversation in between. So that's for people who are not down to speak, that's your chance to interject and influence things. So just one, before we get going, just one thing about the kind of nature of this, because some people may be wondering, why is Health Data Research UK doing this? We've got a lot of funding. We've got 5 years of research to do. We've got a lot of healthcare and medicine to get through. Why are we worrying about this? And I was wondering how to explain it to folk. And Frank Van Harmelen may like this, because I know Frank likes Tom Waits. I like Tom Waits. I don't know how many people like Tom Waits as a musician. I think he's absolutely brilliant. He's my favorite. And so Tom Waits plays a lot of different musical instruments, actually. Very accomplished pianist, guitar, but he plays a lot of musical instruments. In the middle of his career, he started making his own out of junk and so on. And then people asked him, he said, why, Tom? Why are you making new instruments to play on? Because that's obviously you'd be better off being more like concert pianist or something, just learning a lot about your own one. And he said an interesting thing. And the interesting thing he said was the trouble with playing the same instrument all the time was that there's a kind of muscle memory, and your fingers always went to the happy places of where you were playing the music. And if you kept doing that, you'd never play anything really original and new. And I thought that's a very Tom Waits thing to do. And for me, digital healthcare is a bit like that. If you keep playing the old instruments, you'll be in the happy place for a long time, but you may never play anything really new. And the problem you've got then is that instruments on which you play are going to be very, very different, I think, in the coming 5 years or so. And so that's why I've invited the sort of people that I've invited to this particular meeting. It's deliberately chosen to be people who can talk about the things that are headed towards us rather than the things we're familiar with. So that is AI, machine learning, exascale, quantum, and then people from within Health Data Research UK more towards the afternoon talking about their experiences of that. So it's very much a looking forward type of session. And when people are talking about this, that's a good way to think about the questions that you might ask. We should always be looking to the future rather than talking a lot about what we've done, which we do a lot anyway. So that's basically my attempt to set the tone of this. And we've got very prestigious people looking in. I see the new president of the Academy of Medical Sciences sitting there beaming benevolently on the proceedings. Hello, Andrew. I'm glad, good of you to make the time. So we've got quite a lot of good people here. And I'm watching the time, and I've used up most of mine. And so to kick us off, actually, we've got Frank Van Harmelen from Amsterdam, and Frank, sparing his blushes, I would say, if I had to choose someone with the kind of best broad knowledge of AI and experience and balance, I choose Frank, which is why he's here to kick us off. So no pressure, Frank. If you can kick us off with your talk, that would be great. And I'll leave you to take it away.
Okay. Thank you, Dave. That's quite a challenge you've set us. I'm really honored and pleased to be here, and great that my long-term colleague and friend Dave hasn't forgotten about me. So I'm very happy to be here and trying to talk about something that is really coming towards us indeed. So the title is Hybrid Intelligence Systems that Collaborate with People Instead of Replacing Them. But an alternative title of the talk could have been Hybrid Intelligence, a Research Agenda. right? So I will be mostly talking about open questions and not so much about things that we have already achieved. I mean, some of it, but there's a lot of open challenges here. This is very much in keeping with the introduction that Dave just gave us. I'll be talking about the Hybrid Intelligence Center, how we organize this a little bit later on. But first, let me remind you of what is the classical perspective in AI. The classical perspective in AI is the automation perspective, right? And I've just taken two famous quotes here that capture the automation perspective in a medical setting, right? So this is Andrew Ng from, at the time, still in Stanford. He's now elsewhere in Alibaba in China, saying in 2016, saying a highly trained and specialized radiologist may now be in greater danger of being replaced by a machine than his own office assistant. Okay, so this is 2016. Well, as far as I know, not a single radiologist has yet been fired because they've been replaced by a machine. Or around the same time, Jeff Hinton, people should stop training as radiologists now. It is just completely obvious that within 5 years, deep learning is going to do better than radiologists. Okay, so there is this deeply ingrained view in AI about we improve AI and then we can move the AI in and we can move the people out. And that's not just true for medical staff. I could have had quotes here about self-driving cars, no, self-driving car in, Uber drivers out, Google Translate in, interpreters out. This is very deeply ingrained in the classical view of an AI. And this dates all the way back to the Turing test, right? So the Turing test is, can we spot the difference between a human and a machine? And if we can no longer spot the difference between a human and a machine, then we must conclude that the machine is intelligent, right? Because we think the human is intelligent and we can't spot the difference. So again, this is the automation perspective. This is the replacement perspective. But strangely enough, AI is rather unique in this. Most of the technology that we develop in other fields is not the automation or the replacement perspective. We don't try to imitate what we already have. Now, why would we build machines to imitate people? In other fields, we don't do it. Now, imagine what would have happened if we had built planes to imitate birds, right? Then all our planes would have been like this. Okay, and clearly our planes don't fly like this, and just as well that they don't fly like this. So the best way to build flying machines was to not imitate natural flying. And maybe the best way, the most interesting way to build intelligent machines is not to build and replace natural human intelligence. So this suggests that this idea of replacing humans by machine is a little bit like trying to jam a square peg into a round hole. They are just different shapes. They may well end up being very different shapes. And then replacing one with the other is simply not the right way to think about it. So we should really abandon this automation and replacement perspective that has been there from the very beginning. And indeed, now, if you look at the history of human science and technological inventions, now, all the way going back to the invention of the fire, the invention of writing, the printing press, the steam engine, the computer, the web, none of these replaced people. All of these augmented people. All of these improved our facilities. They increased our memory, they increased our muscle power, they increased our brain power, they increased our communication power, but they never replaced what we did. They augmented what we did. So I'd like to tell my students that AI doesn't really stand for artificial intelligence, but that AI stands for augmented intelligence. Okay? We don't even need to change the acronym for this. And this is not just me telling you this. Here is a quote from already a 2018 report, right? So this is almost 6 years ago, where Deloitte, the expensive consultants, they write, already at the time, it is better to view AI systems not as thinking machines, but as cognitive prostheses that can help humans think and act better. Okay? So this is the perspective that I'm after with augmented or hybrid intelligence, where hybrid stands for the hybrid collaboration in a hybrid team between human agents and machine agents. That's the hybrid aspect of hybrid intelligence. We're investigating this in the Hybrid Intelligence Center in the Netherlands, which is a 10-year funded research program. We are now nearing our midway point. We have, I never thought in my life I would say the next sentence. We have 30 PhDs working on this across the country in the first cohort, and 20 more have just joined us in the second cohort. And what I will be doing in this talk is to speak about the research challenges that we are trying to address. And again, this is more about the challenges than about the answers. So the research agenda that we have organized is in organized in 4 parts. So in order for AI to be hybrid, to function in a hybrid team, it must obviously be collaborative, right? It must be able to collaborate. It must be adaptive. It must be able to adapt to changes in circumstances, changes in tasks, changes in team. It must behave responsibly. It must be aware of our norms and values. And of course, it must be explainable, right? Imagine collaborating with a colleague that never explains what they're doing. That will be very, very hard. So this CARE acronym organizes our 4-part research agenda, and I will talk about some of the parts of this research agenda, not all of them. Now, we want to stick within the time, but I'll talk about some. So let us start, and all of this is based on a 2020 paper we wrote on with this title, A Research Agenda for Hybrid Intelligence. This had a serious impact. This is now sort of routinely quoted as, yes, this is a research agenda that we should be moving towards in AI. It got the Paper of the Year award for the IEEE Computer Journal at the time. So let us go through some of those elements of the research agenda. Let's start with the C of our CARE acronym, with the C of collaborative hybrid intelligence. So I want to start by giving you a brief example from collaboration between humans and computers in music in the form of a short video. And Dave, can you put up your thumb if you can hear the sound properly?
The system will try to learn my chord style and my bass style. So as after a while, I play a trio. I will play only the melody after a while. And then you will hear a bass and chords, but you have to understand that these bass and chord, there is nothing pre-recorded now. It's only extensions of my bits of playing there. So let's try. I will play more chords.
So the bass line, the background chords is all improvised by the computer.
And so all these different ways of playing the same chord, the same chord structure, are triggered by the things I actually play. So it's not a recording; it's a style which is being developed as along me when I play. It's very different because then I have the sensation to play with someone.
So you are playing with a copy of yourself playing the bass.
Yes, and a copy of myself which is listening to me and trying to adapt to what I play and the way I play.
So you call this project a virtual band?
Yes.
And that's really what it is. Could you imagine performing for a live audience with a virtual band?
The ultimate validation would be one day to do a concert myself alone with the system, which would not be boring.
So this is not a matter of, oh, we can automate musicians and then AI in and musicians out. This is really a collaboration between a human and a machine. And music is not the only area where this happens. Another great example is in centaur chess. So some of the best chess players now are no longer people. We know this since Kasparov lost from Deep Blue in '99. But some of the best chess players are also no longer computers. Some of the best chess players are now combinations of humans and computers collaborating on playing chess, the so-called centaur machines, which are half man, half machine. What is needed for such collaboration? Well, one of the things that we do in collaboration is very routinely as humans, we do mind reading, right? It's what psychologists call, we have a theory of mind. We have a theory of the mind of our collaborators. And here's a very simple movie that shows you what theory of mind and how well it works, even in a 4-year-old.
Oh. Oh.
And here's where the mind reading starts. So it's important to realize not a word is being spoken here, right? There is no instruction. There is just mutual understanding of each other's goals and proactively acting to facilitate each other's goals. This is really collaborative behavior. Now, how could we make such a theory of mind computable? How could we implement this in computers? And actually, there is a large body of work in symbolic AI, in logic, where people use what's called epistemic logic, where we could say things like, well, if P is true, then I know it. Or if I know P, it must be true. Or more realistically, if I know P, then I know that I know P. And so this is a logic that implements not just what is true and false, but what I know to be true and false, and what I know that other people may know. So we could index this with the saying, oh, well, I know that you know that something is true. So this is a step towards a computational theory of mind, which would be an essential ingredient for computers collaborating with us. And this is an example of the kind of new questions or the different questions that you will have to ask in AI if you move towards hybrid intelligence instead of automated artificial intelligence. Right? These are not questions that are at the forefront of current AI research, right? But these are the kind of questions that we will have to ask if we move towards collaborative computers. And we do computational experiments with this. We show in game-like settings that that machines with a theory of mind perform better, both in cooperative and in competitive settings. So if we design games where you win by collaborating or games where you win by competing, a theory of mind helps. Another thing that we do is we communicate multimodally. We don't just communicate by talking, but we communicate with our faces and with our arms and our body. And this is a crucial ingredient in human collaboration. In hybrid teams, machines will have to be able to interpret our facial and our body expressions, including what those expressions say about intent and belief and state of mind and so on. So again, now these are the kind of questions that we will have to ask ourselves in AI if we want to be serious about collaborating with machines. And in our research, we do this in increasing stages of difficulty. So we increase the challenges for the machine. So it's rather easy to collaborate in a group of 2. It's just me and the machine. It's much harder to collaborate in a group of n, where n increases. Right? It's easy to collaborate in a group where the membership is static. I know in advance who's a member of the group, and they'll stay with us till the end of the task. Real teams change all the time. People drop out, people drop in. The roles in the group change. Even during the collaboration, the roles of the group change. Sometimes the roles are allocated, that's the easy part. Sometimes the roles are negotiated, that's harder. So there's all these different dimensions along which we can make this research challenge harder. If you look at current human-in-the-loop AI systems, they take more or less the simple choice on every dimension. It's collaborating between one person and one machines, in static roles, in fixed groups, on allocated, pre-allocated roles, in a hierarchical structure that doesn't change, right? What would happen, what we would need to do if the collaboration between humans and machines would need to become as fluid and as fluent as it is now in collaboration between humans. So here are a number of the questions we will have to start asking ourselves: computational models for negotiation, for agreement, for delegation, computational theory of mind, multimodal messages and expressions. Now, these are, many of these are not at the forefront of current AI, but I think they should be if we really want to move towards collaborating with people instead of collaborating with computers instead of having them replace us. And I may add, we may well be looking at a revival of some of the classical techniques of symbolic AI in combination with the more modern techniques of statistical AI, rather than putting all our eggs in the statistical large neural network basket. So let's do this again, but for a second part of our research agenda, let's look at how to get systems adaptive. Right? Of course, in collaborations, our collaborators, in collaborations, we constantly adapt to changes in the environment, to changes in the team, right? There is an inherent tension between adaptability and reliability. It's very easy to build safe systems if we know in advance that the system isn't going to change. It's much harder to build a safe system if we allow the system to adapt to changing circumstances. And there are a number of techniques around transfer learning, multitask learning, meta learning that begin to address this in the modern AI research agenda. And one in particular is reinforcement learning. With many of you will be familiar with this. So what does reinforcement learning do? An agent performs an action in the world. And as a result of that action in the world, two things happen. It observes the results of its action, and it gets a reward signal, whether that result was desired or not. And by going through this loop repeatedly, an agent is able to optimize its actions so as to maximize the reward function. Now, what happens if the world changes? Right? Well, if the world changes and the agent performs an action, then the reward signal will change, right? And the world is now different. So the observations of the results of my actions change, the value of my reward function changes, and I automatically learn that I should do other actions. So reinforcement learning is a very natural paradigm to think about learning in a changing world, which is very different from the standard batch-based machine learning that is the currently dominant paradigm. But current reinforcement learning requires a lot of work to make it suitable for hybrid teams in which humans and agents collaborate. So we want to learn reusable behaviors, patterns of behavior that can reuse in different circumstances. We want to guarantee that we are learning safe behaviors. Current reinforcement learning methods are insanely data hungry. Now, we cannot afford to make a million mistakes before we properly learn the right behavior. We need to do this with much fewer trials. There's a very interesting experiment a few years ago where people from UCL and DeepMind ran a reinforcement learning agent, but they combined a symbolic and a neural a part of this agent, where the agent was not learning end-to-end from directly coupling observations to actions, but the agent was building an internal mental representation of the world. So that the world was a grid world with these crosses and zeros. And the task was to collect all the crosses and avoid all the zeros of the agent that had to navigate in this grid world. And the classical end-to-end trained agent did very well, the blue line. But as soon as you start changing the world, then the agent would start to benefit from having an internal, symbolically described representation of the world. It would become much better at adjusting to changes in the world. Whereas the end-to-end learning agent would have to relearn every time the world had changed. So I think this is a very interesting example of how AI paradigms will have to change if we are moving towards collaborative and adaptive AI. And in the last few minutes of the presentation, because as Dave said, we won't have ample space for discussion, I want to show you what we are doing in the Netherlands is in one of our case studies in the Hybrid Intelligence Center. And I've picked one from the medical domain. This is robot-assisted microsurgery. And this is work together with Dr. Dalibor Vasilic from the Erasmus Medical Center in Rotterdam. So what is the setting here? The setting here, so what is our current, let's say, the surgical universe that we're operating in? Well, an important part here is actually a picture of Dalibor on the right. This is a microsurgeon. The microsurgeon are the surgeons that whose job it is, to stitch nerve ends together, right? And by the way, a nerve is thinner than a human hair. Now, these are highly trained and highly specialized people. It takes 15 years of education, but even after 15 years of education, even a microsurgeon is still human. And they have all these cognitive and physical limitations. One of the limitations is that it's very hard to actually see what they are doing because what they are doing is so small. So instead, they are not looking at the location of the surgery, but they have a camera look at the location of the surgery that enlarges the image, and the surgeon is looking at the screen. So this is the setting that Dalibor is operating in. He's looking at the screen while operating on the patient that is lying on the table. There are cameras which help him to focus on the area where he's doing the operation. In fact, they bought a state-of-the-art a robotic microscope. So this is a robotic arm that can move in 3 dimensions with a large number of degrees of freedom. You can talk to the robotic arm. Dalibor can give the robot instructions. The robot can even do automatic instrument tracking. So if Dalibor is moving his pincers or his scissors, then the camera can track the instruments, and Dalibor can speak to the robot and say, no, move 10 degrees to the left or zoom 15 degrees out, and so on. So this is off the shelf. They bought this from a company in Canada, right? And this is a complicated setting, right? So this is the operating theater where we have, of course, the patient, we have the surgeon, but we also have the anesthesiologists, we have a technician, we have a scrub nurse. So this is a complicated environment, a hybrid team where the robot arm is supposed to collaborate with all the people in this hybrid environment. And this is a quote from Dalibor when in 2020 they bought the robot. The quote is, we are so enthusiastic about the possibilities of this new robotic arm that with the support of the executive board, we bought the first digital surgery microscope in the country, right? Front page news in 2020. 2 years later, we had a conversation with Dalibor. What was Dalibor saying then? He says, this robot, it doesn't adapt to me. I have to adapt to it. It doesn't understand surgeon speak. I have to talk robot speak. The surgeon doesn't know what my operative plan is. It doesn't know what I'm going to do next. It doesn't know what it should do next, right? Please, can the hybrid intelligence people help us to build a surgical platform that collaborates with me instead of me having to adapt to it? Okay. So we instrumented the entire operating theater. Every yellow patch you see here is a camera that is observing what's going on. And the challenges that we are now in the middle of solving are things like, how can we equip the camera, the robot camera, with a theory of mind of Dalibor, so that the camera knows what Dalibor is doing? This is not just the fixed plan, because Dalibor is changing his plan as the operation is going on, because some things are not going according to plan. Dalibor is changing. How can the camera predict these changes in plan and act accordingly? Right? How can Dalibor and the camera have a shared world model so that Dalibor no longer has to say robot speak, like move 30 degrees to the left, but that Dalibor can say things like focus on my left hand, right? How can we make the camera aware of the different roles and what the different responsibilities are? As I mentioned, the operation plan is often changing during the operation, even though the operation has been entirely practiced in the day before, right? So how can the robot adapt to the changing plan? So this is an excellent setting where we really want to build a hybrid intelligent robot, the robot assistant camera that collaborates with the surgeon. And this is very far from, and not at all intended to replace the surgeon. So now, given with an eye on the time, this is where I want to leave it. I would be very interested in the rest of the conversation to hear if you see your healthcare challenges for hybrid augmented intelligence rather than automative artificial intelligence. Thanks for your attention.
Great, thanks, Frank. So people can you have a choice, I believe. If you want to ask questions, you can put something in the chat and I'll try and pick it up because I've got my eye on the chat. Or you could surface in the sea of faces in the Zoom meeting and put your hand up and try and get attention that way. While you're thinking about that, I'll start off a little bit. So Frank, one of the things that I think on people's minds connected with HDR UK and in general in digital healthcare is to do with systems. So a lot of what you talked about, so you explained it in AI terms, a lot of it is systems engineering. So do you have any intuitions, maybe from the stuff you've done or just in general, about how some of these systems can actually come in? Because you are asking systems to change, sometimes people, but certainly systems to adapt to this. And healthcare is one of the, at least maybe this is my personal prejudice, is one of the most resistant systems to fundamental change I've seen in a long time. So how do you get from where we are to where we might be with some of these systems? Any thoughts?
Okay, so first, let me plead ignorance and say, I'm only a simple computer scientist. Okay, so I'm naturally on the systems, on the technical system side of things. What I notice at least in the Dutch setting is that there is a lot of interest in implementing these changes the lower you go down in the hierarchy, right? So on the operating theater floor, everybody is very keen to get this going. We're doing this also in another project on lifestyle interventions for diabetes care and prevention, right? All the public health workers that are involved there, they're all very keen. The higher you go up the hierarchy, the more perverse the incentives become, right? So there is sometimes not an incentive for diabetes prevention because hospitals get paid per intervention. So fewer interventions actually means fewer income for hospitals. So I think much of the resistance is higher up in the bureaucracy and the organizational hierarchy rather than on the factory floor, so to speak.
And another question that was in my mind. Oh, no, sorry, I will stop. I tend to monologue, as some people know. So John Connolly has raised his hand. John, do your thing.
Sure, thank you. Hopefully you can hear me okay. I'm in quite a busy office. That was a really interesting presentation. And really my question is when we're thinking about these sorts of hybrid systems, and my question really is about performance evaluation, because many of these systems are likely to meet statutory definitions to be medical devices. And how do we or in your view, how do we demonstrate consistent performance in terms of effectiveness and safety for the intended purpose, where there is that hybrid element of both the kind of AI, but also the human element, there may be some performance dependence. It wants to be really good to get your thoughts on that. Thank you.
Yeah. So I think you put your finger on a sore spot. So in particular, so let me pick the adaptivity of the system. Okay, so we've been working together with Philips, they sell these large scanners, right? And there's a lot of machine learning in these scanners to automatically adjust the settings and already pre-interpret and filter the images and so on. So they have a trained machine learning component in the scanner. They get the whole thing validated and certified. And now they're going back to and then they're saying to the certification agency, oh, and by the way, our machine is continuously learning and continuously adjusting, right? This does not make the certification body happy. Okay? So I think there is a real tension there between systems that continuously adapt versus systems that are frozen in time in order to get the certification.
My question isn't, so that was a really interesting point, and I do recognize the challenge there around kind of continuous learning and predetermined change and so on, but that's not really my question. My question is actually where performance is dependent both upon the human user and upon the AI system and the way those two things are interacting. And so my question really is about demonstrating, maybe there is not currently an answer to this, but how you demonstrate consistent performance in that setting. Maybe, you know, does that require restrictions on the level of training that the user requires, for example?
Yeah, so these are some slides I took out of a longer version of the presentation, is that we designed a set of metrics for each of these dimensions for our care agenda. So for collaborative, adaptive, responsible, and explainable, we designed a number of dimensions and measuring points on these dimensions. So we have been thinking about this. These are not the typical dimensions that would satisfy that will do for the standard AI methods, because they involve measuring the competence of the team as a whole, rather than measuring the competence of the device on its own. And in that sense, you are right. We will have to advance both our vocabulary and our metrics for evaluation. We have to evolve that together with the research agenda itself.
Great. I think that answers that one. Hong Han has his hand up. Hong Han.
Yeah, thanks, Dave. Hi, Frank.
Hi.
Yeah, so I really like the idea of hybrid AI and augmented AI. I learned a lot from your talk. Thanks. So I guess if, say, we're working towards that direction, we need a better way to quantify what AI systems or machines are good at, what humans are good at, and also even model what humans are good at and the machines are good at. I guess all these current systems, people evaluate the performance based on all these metrics, F1 score, precision recall, not necessarily can help us to say what's the better way to augment human or to adapt to human environment. What any thoughts or suggestions in that regard?
Yeah, I completely agree with the premise of your question, that this requires also an understanding not only of the strengths and weaknesses of the systems that we are building, but of the strengths and weaknesses of the people who make up the other half of the team. And so we are working with say, people from social psychology who have been studying collaboration in human teams for a long time. So in social psychology, there is a fairly good understanding of what drives, what helps and hinders collaboration in human-to-human teams. So, for example, we have in-group favoritism, and then we have recency effects. There's all these drivers for human collaboration, and we are explicitly exploiting that knowledge about human-human collaboration in order to adjust it to human-machine collaboration. So definitely this collaboration with social psychologists on this is absolutely necessary.
Thanks.
Already, with your hand up.
Thanks, Frank, for the fascinating talk. I can tell that my camera is working. Good. Fascinating talk. Thank you very much. I was very intrigued by your slide talking about the difficulty of collaboration. And it just got me to think about collaborations that I've enjoyed as a human. So typically that's cases where the roles are dynamic and negotiated. And when there's something new, unexpected, some kind of innovative thing coming out of the collaboration itself. So where I learn from my collaborators, I help them learn from me, and we become better in our roles that are now evolving. How do you think machines could handle that?
Okay, so now is the time to admit the limitations of where we are. So in terms of the answers I gave to John about these dimensions in which we are measuring our progress towards this hybrid intelligence, these teams with dynamically changing roles that were not scripted beforehand, they are way on the far end of that metric, right? So admittedly, our work until now is very much in the realm of pre-scripted roles that are limited and that do not change, well, or that only change within a certain to a certain degree. So I think the robot arm is very clear, right? So the robot arm only has one role, and it's not going to change. Right, and we wanted to adapt, and we wanted to understand, to have a theory of mind, and so on. But the roles are static. We have not even scratched the surface of the kind of collaborations that you have enjoyed so much.
Good. Okay, so I've got I'm keeping an eye on the chat. So there is a couple of questions in the chat. So one is from Satari Majidian. I'll just shout these out myself rather than inviting them. But do pitch in if you want to say something yourself. So a question is how the workload distributed between the surgical team and AI works during the operation. So in what specific aspects of surgery does AI participate? Does it focus solely on diagnosing the location of abnormalities, or does its involvement extend beyond that?
Right. So I think it's maybe even less than you make it out to be in your question. The role of the robotic assistant here is only to drive the camera. And remember, the camera is key because the surgeon is not looking at the wound. The surgeon is looking at the screen that's being filled. But this, because this is the only view that the surgeon has. This view is extremely important. And what we want the camera to do is during certain operations, during certain actions, it makes sense to view exactly from the top, whereas for other actions, it makes sense to have a more of a landscape view. There are known stages in an operation, and these stages have been practiced the day before. And during when moving from one stage of the operation to another, the camera should know what zoom settings or what contrast settings and so on are the best suited for that particular stage. So it should be a camera. It is the role of the robotic assistant is only limited to driving the camera, but to drive the camera in a way that is sentient, that is knowledgeable about what the surgeon needs at every time.
There was a follow-up question connected with that in the same bit of the chat, which is does it provide assistance that's beneficial for both novices and experienced surgeons? So if you put in a differently skilled surgeon.
Yes. So that's a very interesting point. And we're actually doing both at the same time. So we have two teams working on this. One team is building the robotic assistant in the training setting for trainees, and the other one for accomplished surgeons. And we're trying to learn from the difference between those two teams.
I've got another question in the chat from Prokar Dasgupta. He says, is there a standardized way of evaluating hybrid intelligence and reporting its collaborative surgical performance? How do you evaluate this stuff?
Yeah, so our surgeon colleague Dalibor likes to say, well, the only outcome that matters is a patient survival, right? Patient success. Okay, fair enough, but that's a little bit too coarse-grained for us. So we are also measuring things like very easily measurable things like repeated instructions. So currently the surgeon gives one instruction, the camera doesn't get it, they have to say the same thing again. The camera doesn't get it, and they have to say the same thing in a different way. So we're trying to measure the effectiveness, the efficiency of the dialogue. We're also trying to measure the mental load. that the surgeon is under. So we're trying to do these measurements during the course of the operation, apart from, of course, overall metrics like a patient outcome or length of the operation and so on.
Right. Any more questions from the audience? If not, I'll have one tiny one at the end myself. But I don't want to gazump anybody else who immediately wants to ask something. Don't think so. So I get the luxury. So this is a sort of intuition question, Frank. So one of your slides was talking about that sort of question I suppose I would typically ask. Had up the deep learning and friends, that particular approach, which is sweeping the board at the moment, plus symbolic reasoning. And I'm wondering, the subtle thing there is when neural methods and friends start to impinge on what would have been symbolic reasoning. Do you feel a tension there at all, or is it easy to know in your experience where symbolic reasoning should step in and deep learning back off, to put it brutally?
So I think this is actually one of the most exciting current frontiers in AI. I think one of the most at this frontier is exactly this question that you just raised. So I think we went through a period when when we thought, okay, well, neural networks are the answer to everything. I think we're beginning to learn that maybe that's not true. We've also seen that symbolic methods are not the answer to everything, that they have complementary strengths and weaknesses. And exactly finding out what are these complementary strengths and weaknesses. I mean, there's high-level intuitions about this, but this field of what's called neurosymbolic AI, I think is currently one of the most interesting boundaries within AI. So I don't think there's a short answer to that. I think that's exactly one of the most interesting current questions in AI.
Good. Okay, that's a good place to stop and thank Frank for a very stimulating introductory talk. And I see one other thing. I see Darren has put a comment into everybody in the chat. Feel free to put in comments in that way if there are things that you think augment this. I won't mention them because that just takes time and everybody can read the chats. But do feel free to do that if you would like. So thanks, Frank. And we move on almost perfectly to time to Alessandra Russo's talk. And Alessandra, the reason for inviting you is to bring in somebody with deep experience in machine learning, and actually on this kind of edge between symbolic and neural AI, to be able to give us a bit of insight into that. So if you're happy, take it away, and we follow the same procedure.
Yes, hi, thank you. Should I just, let me just go over there. Can you see my screen?
Yep.
Okay, perfect. So I want to try to go in play mode if it's possible. Can you still see it?
Yep.
And a big screen and dynamic going, yes?
Yep.
Okay, fantastic. Thank you very much. And I think actually what I start now is links very well to where we stopped and what Frank was saying and you were saying, David, about this neurosymbolic AI and how we can bring together these two different words, right? So the old classical AI versus this new upcoming AI technology. So, and I come from the background of AI. I'm an AI person and I lead a research initiative in a new campus in Imperial called ImperialX. So the initiative is about developing intelligible AI methodologies. So what this discipline is based upon is developing solutions that can deal with problems such as explainability, safety, understanding, and communication. So this links very well with what Frank was saying. And cross-cutting all these foundations AI advancement are, of course, a lot of application domain, including healthcare. So, and my expertise and my work in my research group called Spike is concerned, but predominantly on symbolic machine learning and neurosymbolic AI. So I'll try a little bit to give you some idea of what these things are. I would like to acknowledge, first of all, my big group here. So these are all my PhD students. I grouped them by different thematics in which we work in my area. and with the support from ex-PhD student, where we actually made advancement in the context of symbolic machine learning. We have now a company, an SME, that actually develops and apply this in safety critical domains. So we try also to put our link with healthcare as well. So I'm interested to hear your opinion on this. Okay, so just briefly, we talked a little bit about the pro and cons of machine learning. Frank was alluding a little bit to that as well in the previous talk. And we know what the big advantage and capability are, and also what the big limitations are. Some of these limitations is inability to integrate with existing knowledge, and there's quite a lot of knowledge, in particular in the humans and the domain in which the AI is applied. Inability to generalize from particular instances and be able to transfer. Frank was alluding to some of these. And also inability that some of these machine learning models are not really interpretable, right? So they are very difficult for humans to understand exactly what these models have actually learned. And it's become even more difficult in the context of these very large foundation models where we have billions, trillions of parameters. So what is it with the symbolic AI? Symbolic AI is really the other side of the coin, and Frank was alluding a little bit to this modeling, this theory of mind. And essentially, these are technologies that not only provide a language for representing this knowledge, but also to reason and to learn this kind of models. So there's a lot of advancement done in this area, and we should not forget about all of this. And there are the particular advantage of this technology are the fact that they have rigorous semantics, so they can have some provable guarantees of the performance. They are interpretable to human, and they are not necessarily data thirsty. They are very data efficient, and they can integrate some prior knowledge. So as you can see, these are literally two faces of the same coin. So what's at disadvantages? One type of domain of AI, we find advantages in another type of domain of AI. So really the step forward that we're actually working on and people are starting gradually to realize is we should build upon solutions that combine this different technology in order to basically take advantage of the limitation of the respective capability and overcoming the respective limitations. So from the point of view of cognitive science, I don't know whether you're aware, it is a book called Thinking Fast and Slow, this idea of modeling the human mind in terms of a capability of thinking very fast from the real world and have a kind of a quick perception that this is what, if you like, machine learning is capable of doing very well. But also human mind thinks in a more logical sense, slowly when it do planning, when it has to adapt, and when it has to make hypotheses about situations. And this is more like the symbolic aspect of AI. So we really wanted to combine these two and create neurosymbolic AI solutions that can go really beyond this idea that intelligence is just recognizing patterns in data, right? Or approximating functions, which is essentially what machine learning tend actually to be doing. So my research is in this field, and I want to give a little bit of some intuition of what the symbolic AI is, because I think there's a lot more hype on the machine learning aspect more recently, and show you the advantages of this symbolic AI system and the advancement that we have made in this field, and how we can actually combine some of these two different words. So neurosymbolic is becoming more and more a very so a realization that actually we needed to have a combination of different technology when we wanted to solve complex problems. And typically, some of the applications are in applying symbolic reasoning mechanism together with a differentiable or more, machine learning approaches. So, for instance, recent paper in 2021 was how we can improve the coherence and the consistency of what a large language model, like ChatGPT, could actually provide by using a symbolic checker that actually perform as a kind of a wrapper, verifier wrapper around the performance of the foundation models and actually determine whether the outcome or the answers that the model gives are correct or not. So this is symbolic, neurosymbolic reasoning, really, because we have to have this wrapper symbolic model around it. So similarly, another very recent, even more recent application is this work about so an architecture that solves logic inference steps, and try to do that in combination with large language model for processing text and natural language description of problems, and then use this symbolic engine field improver that actually construct the reasoning steps, right? And these are more provable, they are more robust, they have more provable guarantees. And they help extracting information from this hybrid system that is also that is also more robust in the predictions. And another third interesting application is very recently, for instance, DeepMind has published this work called Alpha Geometry that actually shows how you can combine large language models with, again, field improvers specifically tailored for proving solving geometry problems, and have demonstrated how this can actually enhance the performance of these AI solutions, this AI system. And they actually perform much better than if we use just the large language models. So this is just some examples of where you can see that actually machine learning and more recently this large language models, foundation models architecture can work together in sync with symbolic AI that help reasoning and checking the correctness and also guiding the search of these large language models. So that is the spirit in which actually I believe AI is moving towards, and there is more and more realization of the advantages of these combinations. But what is common about all these three examples I put up here is that the knowledge or the symbolic model that is used in this architecture are actually manually engineered. So the field improvers to be manually engineered, and the knowledge for checking the consistency in a particular domain is manually engineered. So the question really that we actually want to ask, and that's why the advancement done in symbolic AI is actually quite promising, is how can we actually learn this knowledge, this symbolic model automatically in order to allow this model to adapt to changes in which this neurosymbolic system are actually applied, all right? So the question we try to tackle here is, can we actually learn these symbolic abstractions that will help to guide and control the consistency and the coherence and the performance of our machine learning in an automated fashion, right? And how can we do that also in combination with humans? So this is not completely fully automated, right? So this is essentially where symbolic machine learning comes in, and really is an area of AI that combines together the symbolic classical approaches to knowledge representation with actually the machine learning mechanism that I was just describing. And but what the advantage of this area and field and systems are is they can actually learn this complex knowledge and models written in a way that is interpretable to human, and they can learn it also from a very few data points. They don't need to have large quantity of data to be able to abstract away complex knowledge. They can take into account existing domain knowledge. They can generalize from examples, so the model that we learn are more easily transferable. And the model that would be learned can also be explained and verified and giving some kind of provable guarantees. So I'm going to give a little bit of some example about this symbolic machine learning solution, and then I'm going to show how this is related also with machine learning, other aspect of machine learning that we just talked about. So before, up to a certain point, the symbolic machine learning was a very at its infant step, we can say, right? And we done in our there were three major limitations that people perceived that when it was a hard problem to be able to learn knowledge that is complex, that is abstract, and from data, right? And the people were thinking that when we talk about knowledge, when we talk about logic, when we talk about symbolic, we are not really robust to noise, and data are actually very noisy. So this is one of the big, so if you like, a criticism that this area had in the past, and also the fact that they are perceived as to be not very scalable. So we actually expanded a lot this area of symbolic machine learning, and now we are at the forefront of of this field, and we developed systems, a plethora of systems and algorithms that can actually address all of this criticism. And I'm going to give you some little bit of examples here and there about what we can do. But just before getting to a more detailed example, let's give you the general intuition about how this system can be used, right? So imagine here that you have a video, and this video is actually annotated, is processed by machine learning with things that happen in this environment. And the task in this context is, for instance, learning general conditions under which an event, such as people meeting in this particular environment, occurs, so starts and ends, all right? So we have all this series of video clip. Now, what we can do, we can process this with the machine learning algorithms for videos very easily and try to extract some symbolic features that determine the characteristics of the object, or maybe also object tracking. Frank was referring to activity of the people in the video. So this is like contextual information. And we have to take some kind of labeling, so because we need some form of labeling. So symbolic machine learning is a form of supervised learning, we say. And so the label in this case is when actually pair of people meet and don't meet in certain circumstances, but this can be applied in any other situations of event detections and so forth, self-driving cars, and so forth. And really, we want to try to learn from this particular program that can decide when an event occur and when actually finish. But together with this data, we can also inject a very common sense knowledge. So we can say that something is occurring at a particular time point and hasn't occurred before. It means because it hasn't been initiated in between. And similarly, it might have been terminated in between. If it occurred before, it doesn't occur after. So this is a very general common sense. Human beings work with this common sense knowledge all the time. And we don't need to learn this from data. We can actually inject directly this knowledge into our systems and take into account these very general principles of behavior, right? So if we take all of this information and we take this data set labeled like that, our system is essentially learning from our data point definitions or conditions under which this particular event, which is meeting or no meeting, is actually taking place. So consider the data and try to optimize and learn a possible hypothesis, if you like. And as you're learning, you can actually show this hypothesis directly to human in natural language. So human can actually see what the system is actually learning. And by learning these general solutions, the system is trying essentially to maximize the data that it has, and at the same time balance this optimization with also learning a more general program. So this is what is called the Ocker principle. So the idea that what the model that you learn is to be more is to be compact, the more compact is, the more general it is. And this balancing of optimization criteria is very important to make sure that what is learned doesn't necessarily overfit the particular data. So it helps the principle of transfer of the general program into other contexts and other situations. So this is quite, the fact that it's explainable automatically is quite interesting. It's a state-of-the-art system in machine learning, in symbolic machine learning. And we kind of, if you like, we extend it as much as we can do. We're working on the scalability also of this. And when we're learning this kind of model, we can actually use this to detect things happening in other circumstances, in other videos. And as we detect, we can also generate at the bottom of explanations, right, of why this particular event has actually occurred. So this is the idea of the symbolic machine learning. So it's abstracting from data, learning general programs, and explaining these general programs automatically in English so that the human can interact with the system. So how scalable this is, for instance, in this particular application, we were having a search space of possible solutions, which was of the size 2 to the power of 44. So we had a 2 to the power of 44 possible conditions, possible rules, and the solution is an element of the power set of that. So really, we are scaling up this quite substantially. Now, to give us some idea about a more complex knowledge that we can learn, this is a little bit more mathematical, so I apologize a little bit here. So suppose that we wanted to just decide whether a certain graph, a certain structure, have got a certain particular properties. Here, the property that we're actually looking for is the property that the graph has to be Hamiltonian. So Hamiltonian means that you can start in one node and you can traverse all the possible nodes, exactly one, but all the nodes in the graph. This is a very complex NP hard decision problem. So, and the people were thinking that symbolic machine learning is really not capable of solving problems of this kind. So in this particular situation, for instance, in this slide, we feed the system very few examples of what we feed are graphs that have this particular property, and examples of graphs that don't have this particular property. For instance, this is not a Hamiltonian graph. And we have some very general background knowledge to say, okay, we're talking about graph, we can have up to 4 nodes, there can be edges or not in the graph. So this is very general contextual information. So if we just give this kind of very few little examples, I want to show really the power of this abstraction that the symbolic machine learning can do from very few examples, right? So even by giving these very few examples and this very limited contextual information, we can actually learn a very general definition of a program that help deciding whether any graph given of any size is actually Hamiltonian or not. So don't ignore the more technical part here, but if you look at the actual description, we can generate from this data a text description that says, okay, any graph is Hamiltonian if, and these are the particular conditions that actually satisfy the property of being Hamiltonian. So, and that was very interesting because really, if from very few examples that we can actually learn some very, very complex programs that can make very complex decisions, solve NP-hard problems. And the interesting bit is that these programs that we learn are not necessarily just needed to make a decision, but can be also used for generating is good distances. So you can use this kind of learned solution to also generate data that satisfy that certain kind of property. So we can automatically generate all possible Hamiltonian graph of any kind of given size. So it's a kind of generative program. Now let's look a little bit about the noise aspect. So the example I gave before, we have a correct labeling of a graph as to be exactly Hamiltonian or no Hamiltonian. But in real life, data don't come with exact labeling, right? So data can be noisy. So when we learn this type of models or knowledge, I said before, we try to balance the coverage with the generalization, with the compactness of our program. Now, if our examples are actually noisy, we might be in a situation that the actual data set is inconsistent. So we cannot necessarily find a program or a solution or a model that cover all the possible scenarios, but we want to maximize the number of scenarios that we're actually covering, or we can explain. So really, the system comes with some optimization function that can be customized depending on the particular domain, taking into account not only the generality of the program that we're learning, so how compact these models are, and how general they are, but also the number of examples that what I'm learning is are not covered, they are not explained. And we want really to minimize this function, right? We wanted to maximize the number the example that we explain, so therefore we want to minimize the example where we cannot explain. So, and this is a scoring function mechanism that the algorithm takes into account to guide its own search and try to get one of the optimal solutions in a given context. So for instance, if we go back to the graph example, and we study what is the impact of noise in learning the complex NP-hard problem, we can actually see that just with the 5% of data, 10% of data noisy, 20% of data noisy, the noise here means wrongly labeling our graph, we can actually get a very high level of accuracy where 70% we already get 70% of data, 70 examples, wrongly labeled, we get 90% of accuracy. So of course, in the context noise, you need a little bit more and more data in order to reach higher accuracy, desired accuracy. So this is really a big sense revolution, I want to call it, a big step forward that we made in the area of symbolic machine learning, because now we are defeating this kind of a preconception that these systems are not robust to noise. And we also compare with other differentiable methods, and we are definitely much better than just pure differentiable method. So one of the characteristics that the system can do, and this relates a little bit with what maybe Frank was saying, collaboration with human, understanding what human intentions are, is actually the ability of learning human preferences, how human make a certain kind of decisions, how we can actually use our system to learn a model of the human behavior, right? So then the system can operate better in collaboration with humans. So classical symbolic machine systems were not able to do that, and our recent advancement has actually provided solutions for this. So imagine that we have a certain kind of preference. This was in the context of intelligent journey planner in a city. And we have a preferred solutions as a different way in going from one place to another. And then we can in general engineer some kind of preference models symbolically. Don't worry about the detail, the technical detail. And having this symbolic model manual engineer, we can actually compute an ordering over the preferred behavior. So you said the preferred decision is this versus this, and that, right? But of course, this is a manual engineer. So what we want to do the other way around. We want to observe the preferences in decisions the human make. So going for a certain direction, picking a certain type of journey versus another, and then extract from these observations what we think is the model, the preference model of the human when he's making decisions. So applying this particular situation capability into this intelligent journey planner, you can think of this as a continuous process, right? So the system has got a particular model, a particular preference of what the human wants, makes decisions upon, and then it suggests the best solution, and with others that are not preferred one, what the system thinks the human will not preferred. And of course, then the human might make a completely different choice, right? So it picks one that the system thinks is not preferred. So by observing these choices the human make, and possibly explanation the human can give as well of the choices made, this becomes automatically a new example for the system, and the system automatically relearn, adapt its own model of the human behavior, and it can continue this process until eventually, if there is some kind of more stable behavior in certain circumstances, the human is able to actually learn this, preference model that the human is actually adopting. So in terms of the current state of the art of symbolic machine learning, we are basically ticking all the boxes for what was supposed to be limitations. And we're actually overcoming now all these limitations. So we are in a position now of really making interesting contributions in this hybrid domain of combining the symbolic AI aspect with more and learning abstract models together with the statistical machine learning and the deep learning. So that's what I'm going to move on now. So what about if data are unstructured? So we have developed various architecture, and we explore a different type of problems. So for instance, imagine you have a neural network that is pre-trained to do certain things, but I want to use this network to extract some features, but I want to use it in order to use to solve more complex problems, right? Not just the classification the network does, but I use this as a tool to extract the features, and then I want to learn a more complex model, with interpretable knowledge in order to solve a more complex, what we call it a downstream task, all right? So, and the question that we asked here is how robust this architecture is, because if I have a pre-trained model and I apply this in a slightly different on a data set which is outside the training distribution, the feature extracted here can be not necessarily correct, right? So how robust is this learning of abstract decision-making models when the features that are extracted from the deep learning are actually wrong, essentially, and also wrong with a high level of confidence, which is even worse. So we did a lot of experiment here in the context of some neurosymbolic data sets. So this is, apologies, not in the area of healthcare, but it's another domain in neurosymbolic AI. For instance, we want to learn a general model about solving a game, a card game, understanding the rules of a card game. And so we have a pre-trained network on a normal deck of cards, but then we have a lot of different type of input images that can be completely corrupted from the distribution in which the network has been actually trained. And the question is, how good is the model that we are learning, these general rules of the game? Can we still learn how the game works, right? If the network is feeding to the system complete wrong prediction, labels of this particular object, features of these particular images. And actually, we compare with many different baselines, which are pure differentiable, including also random forest, and increase the number of data that we give to this more differentiable method compared to our data. And if you see the top lines are all our system, our hybrid system, compared to all the other baselines. So we can maintain a level of accuracy in learning these abstract models up to in the range of 70 to 90% of data fed into the neural component, if you like, which is outside the distribution. So 70 to 90% are wrong prediction. So it's sufficient to have a very few points. They are correctly predicted that the symbolic machine learning can learn very abstract definitions, very abstract models here to make decisions. So the second question that we ask in neurosymbolic is, can these two things actually interact with each other? Can we actually train a network at the same time, also learn this abstract model? This is a very difficult task because there is nothing that is stable in this architecture. The learning of the network happens as the symbolic abstraction is actually computed. But we actually created an interesting advancement here, and we have some architecture that are actually able to do that in some reasonably, interesting tasks. Here there are more mathematical tasks that we're dealing with. So how can we do addition? How can we do the current addition? How can we do multiplications and so forth? And again, our performance is much better than the performance that we can see if we only use purely differentiable models. And the program that we learn are all expressible in English back to the human. All right. So there is also now a possibility here. This is still in its infancy step, but there is some promising result that actually this different system in a hybrid AI, where hybrid for me means different AI solutions, can cooperate together in order to overcome data, in order to be able to learn from very few data, overcome and create explainability and have transfer learning and provable guarantees. So this is quite an interesting advancement that we made. And just touching upon one more example of neurosymbolic AI is referring to, Frank was referring to reinforcement learning before, right? And how the reinforcement learning adapt, which is a very good framework for agent or exploring environments and learning best actions in order to maximize rewards. Now, if you look here, this is what Frank had in his image, diagrammatically speaking, and this is the reward, right? Now, what we actually have, what we actually are looking at, how can we learn a more complex reward functions, right? That determine the structure of a task that the agent has to actually solve. So can the agent abstract away from what is observing and understand the decomposition of its own task in order to be able to take this abstraction and reuse it in other environment. So imagine, so this is a kind of a mechanism called reward machine in the context of reinforcement learning. Imagine your agent is exploring a particular environment, generating traces of execution. And now from these traces, which some that are successful, some that are failure, you can actually learn an abstraction of the general task decomposition. And the agent itself will use this abstraction to then learn its own policy in terms of what is the best action to perform in the environment. So here is the reinforcement learning algorithm talking together with a machine learning, a symbolic learning algorithm. They abstract away from the detail of the environment and learn a model that is interpretable and robust, and they can explain exactly how the agent has solved the particular task. So what is the task decomposition? So these are all, it's under interesting area in neurosymbolic reinforcement learning now, this is called. And we compared in two different domains where we have a discrete state exploration and continuous state exploration. And the comparison is between a task decomposition that is learned automatically by the symbolic machine learning versus one that is engineered by human. And we actually approximate exactly what we human would have done if we had to decompose this task manually when it has to develop or implement this reinforcement learning algorithm. So this is getting closer to do something that, approximate as well, what a human would do. Okay, in summary, so symbolic machine learning have made giant steps. We are getting closer to an ability of learning very complex knowledge that take into account also, I haven't shown this, there's a lot more I can tell you, but take into account also temporal and causal dependency. And the knowledge that we actually learn are interpretable, they can be automatically explained to human. And the neurosymbolic AI can take advantage of this, and combining all these advancement in symbolic AI together with the advancement that we have in machine learning, deep learning, and so forth. And I cannot, leave it without talking about language models. So there is a combined one next step, of course, is how can we use this symbolic machine learning together with foundations models, right? So, and I think one of the next steps that we are currently working on is how can we control, I'll open all the slides, how can we control these large language models in what they generate in a way that take use of symbolic knowledge, right? A symbolic abstraction, constraints, symbolic property that apply in certain domain. So what we are doing at the moment, we're looking at what is called autoregression mechanism or large language model, which is the mechanism by which these models predict the next token, and then generates your final output. And we're looking at this autoregressive mechanism as a search space. And we are considering architecture where we can actually constrain this search space in a way that the outcome that the large language model generate will comply with certain kind of general property. So imagine this is a standardization context. You have a general property constraints that maybe you have also learned these standards, right, through experience in the past, but you have a definition of these constraints, and we can actually control the behavior of our large language model in a way that what it generates is consistent with these general constraints, right? So we can guarantee that the behavior meets the standards in a sense. So this is really ongoing work because this has not been done at all. It is an interesting future direction. And in this case, the example I brought before with the papers, where the knowledge was engineered, the constraints are engineered, this is even one step further. Can we learn that this is a constraint? So then this mechanism is actually continuously adaptable, right? And it's not just engineered once. Okay, so just to quickly wrap up some of the examples that we've done, for instance, combining LLM and symbolic machine learning. We use this in the context of numerical reasoning. So we have large text, so we have some questions which require some kind of numerical reasoning step. You can do with kind of engineering some templates and reasoning templates and controlling that they compose the general question into sub-questions. But actually what we have done, we have automatically learned some mechanism for decomposing questions into sub-questions, using large language model to solve the little sub-questions, and then learn a mechanism for recomposing together the outcome into a more general program, and be able to do this not only just in a numerical setting, arithmetic setting, but also more general setting. So this is one of the interesting advancement that we are also doing in the context of large language model, foundation models, and neurosymbolic AI. Now, just briefly about healthcare, I have a couple of slides. I don't know how I am with time. Just briefly about healthcare. I'm collaborating with people in Imperial who are medical informatics, working in particular in the area of primary care. So, and what we're looking is at the problem of developing a decision support system that can help making decisions about diagnosis in primary care setting. So the problem that we're looking in particular is how can we use information that is hidden in the physician's general practitioner notes. So these notes are normally written in a kind of very quick way that have a lot of sort of, if you like, characteristics in terms of abbreviations, codes, and various aspects of that, which makes them less natural language, for the machine. So, and what we actually envisage is the developing of symbolic, neurosymbolic decision support system, where actually we can make use of information which is in electronic health record of patients, which are more categorical, but as well as physicians' notes, primary care general practitioner notes, and construct some kind of a model about this information, and we call it a knowledge graph representation of that, and use this model together with the health record of the patients in our symbolic machine learning to learn what is some kind of differentiable diagnosis, decision-making model, and use that in order to provide feedback and suggestion to the general practitioner. Now, this can be done cooperatively between the system that is working here and the human, which is the general practitioner. Because if what is learned here is a differential diagnosis model can be explained, which is what we can do, then the general practitioner can actually understand whether the recommendation suggestion is right or wrong. And going back to this intelligent journey planner, can feed back into the system decisions or opinions about the suggestion, and the system can actually continue learning that. So eventually these two components are working together. So we've done some work on the knowledge graph instructions, and we have a mechanism for that. We have a paper in AMIA, which had a Best Paper Award for student paper, and we compared how good it is knowledge extraction versus other machine learning system, and the accuracy and understanding what is in the general practitioner node is much higher with our method respect using other more machine learning method. So that's one of the application. Another application that we're doing is in the context of understanding Alzheimer's pathology. And here we're looking at combining together structural and functional connectivity. And we are trying to think about how we can develop a neurosymbolic AI mechanism so that help to extract the features from MRI and the structural property of the brain together with a functional feature of the brain, and define a model that can predict, in a sense, the advancement, give us some understanding about what characterizes Alzheimer's and what not. So we want really to look at the new clinical biomarker, which are related to both structural and functional property of the brain. So this is another PhD student, but this is a very recent work. We still needed to make advancement on that. And with this, I conclude by giving thanks also to other collaborators. They are the previous picture were my students. These are colleagues, collaborators with which I work. Thank you very much.
Great, thanks, Alessandra. We have a couple of questions in the chat from Sudipta Chowdhury. I think the first one you've already answered, which was to do about the relationship of all of this to healthcare and healthcare-related research, because that was really how you ended.
Yeah.
But then the second question was more towards the earlier part of your slightly earlier part of your talk. But whether this will work, this sort of approach is going to work in complex layered systems where different geographical situations, multiple different agents involved, various uncertainties, unexpected things, maybe some continuous factor added to the object you're studying. All of this sort of complexity, I suppose, Sudipta, you're welcome to jump in and ask the question the way you wanted asked, but I guess this is a question to do with the general horrendousness of the realities in healthcare. How does this actually scale up to that?
So, okay, so I haven't actually touched, I only touched some aspect of the work that we're doing. So the scalability, it's, we've done a lot of work also in the context of, for instance, multi-agents. So we have multiple systems working together, not necessarily in the healthcare domain, so I have to say, in other domains, in the multi-agent settings, where actually you have different agents. They are learning independently but cooperatively together. And we have a project, for instance, where this cooperation is between a human agent as well as a robotics agent, and with the communications between the different agents working together help their individual learning, right? So for scaling up, you really want to address the problem of decomposing so you cannot feed the entire complexity of FKI in one single algorithm, right? So you have to think about the solutions that decompose the problem into different subsystems, and as long as the subsystem they can communicate together and work in sync together. So for instance, the example of the reinforcement learning and task abstraction, task decomposition I showed before, we actually push a step forward. So in the sense that we now can learn hierarchical structures of these models, right? So where each component is learned on its own, but and is actually used by other components. So this hierarchical is the structure that we are imposing, but it does not need to be hierarchical. You can actually push this forward and make the structure much more general. It can be a graph, and then the different component can be the different individual reinforcement learning agent, each one interpretable and explainable. So really, you don't want to tackle the complexity by pushing everything into one single, computational step. You have to engineer that, but the interesting bit is that all these different mechanisms can actually now communicate and interoperate together, right? And I think that's what's good about it.
Any more questions in the chat, or anybody wish to put up their hand? I don't see anything. So I have the luxury of one more question, Alexander. This is a really nasty, difficult question. I'm sorry, but there you are. So the thing about machine learning in healthcare recently is with machine learning, you kind of used to know where you are. I mean, a lot of people were using the method, that sort of things that people were doing was take a particular machine learning method, I don't know, random forest or something like that, take a particular challenge problem, apply it in batch mode to that and get the results out. It was more or less the experimental method. And nowadays, pretty much everybody is offering machine learning. And actually, interestingly, from a computer science point of view, in different ways, some from the machine learning community, some hybrids, sometimes from the database world coming through. And then, of course, industry is piling in with all of this. So do you have any intuition for, I mean, if somebody's working in healthcare trying to start up with this, which some people in healthcare in HDR UK are, my personal favorite, I don't know if he's in on this call, is Richard Dobson's doing lots of work on LLM. Hong Han Wu is doing lots of work, et cetera, et cetera. But what's the best way there's so much complexity now for products and approaches to doing it. Do you have any intuitions for how best to approach this? A good answer could be no, because I certainly have no intuition, but you might.
So approach this in the sense of deciding what system to use.
Yeah, how do you get into it? Yeah, I mean, systems or just general approach to how to get into this.
And deploy them and using or understanding how they work. So that's
people who want to use it practically for their experimental work. And I know this is an impossible question really to answer, but
that's right. I think well, so there are two things. One end, the deep learning method, the machine learning method, some of them are particularly, in a sense, a little bit more advanced than symbolic machine learning method from the point of view of API, right? So you can try different things. You can try and experiment. And actually, the implementation of systems that use this kind of machine learning often are very, very simple. And maybe a large language model can help generating code. So right, they actually say, write me a program that actually learns this, right? And I think it will come. But the problem is that the code it generates might not be correct. So that's something to be seen, right? The symbolic machine learning is a little bit more complex than that. It's less developed from the point of view of API. So in terms of engineering a particular system from somebody who's completely, unaware of it, it might be a little bit more of a steeper curve, to make. But I think that's where interesting interdisciplinary teams, right? So it needs to could be beneficial, right? So it's working together. I think this could be an answer to this.
And I see a hand up now from Satish Kumar Jyoti. Satish Kumar.
Hi, thank you. It was a great work you have done. In terms of symbolic ML, when you're looking into the noisy data, what is the kind of smallest data we can use for training, and then what is the percentage of noisy data that we need in terms of training to predict from?
Yeah, so I think it really depends on the problem that you try to solve, right? For instance, what I showed before with simple problems such as this graph. So for this, in the context of the human journey, intelligent journey planner, let's say, right? So this is really truly something that we did with humans, right? We had we realized that in a real experiment, there were, if you like, 7 or 8 interactions with humans of suggesting something that was actually wrong and then relearning it. So 7 or 8 interactions of this process, and the size of the data was so we learned the first model from sort of hundreds, data in the order of hundreds, and that was not necessarily the best model, right? So if you have this continuous mechanism, then you take counterexamples of the human behavior, and then you learn better and better models, right? So the question is how many times the system has to go wrong to learn the better model. And in that particular context, we had 7 or 8 iterations only of suggestion that were not right, and then the human was actually happy with how the system was recommending. So we actually got the best of the human decision-making models, right? The preference model. So in the context of a batch type experiment, I think it really depends how complex the program is that you want to learn, right? How complex the model is. More nuance they are in the model, and more subtlety in the data you need to have, right? So in order to identify this nuance and discriminate one model versus another. So in the context, you need a little bit more data, and if you have noisy data, depending how noisy they are, so you get, you need to go more and more. For instance, in the case of the cards example, we had, I don't know, 300 data points, right, that with different level of noise within it, and we were still able to learn something. So the reason why these are particularly good in learning from fewer data is because you can actually complement the data with domain knowledge, right? So if you can inject into the system some form of a domain knowledge, the domain knowledge is very abstract, so can in a sense cover a lot of other things, right? Which are, they are going to be true in your particular context, and for which you don't really need the data to tell the system that they are true, right? You can just write in the symbolic way what this knowledge is. So really you only need the data that represent the augmented aspect of the knowledge that you want to learn, right? So, and it's the combination of the domain knowledge with the data that makes the system data efficient.
Yeah, follow-up question maybe. Sorry.
Yeah.
When tried to feed noisy data with the domain knowledge, when you say like a graph, and then so we need to feed the domain knowledge as a graph, or you want that to be as a
No,
text?
the domain knowledge in the case of the graph, for instance, is described as a graph normally are edges between nodes, right? So, and you learn in a domain in which maybe you have a graph can have up to 4 nodes, right? So you can take the domain knowledge can tell you particular contextual information, right? But with general common sense principle, right? In the particular contextual information, and then you actually learn from this domain knowledge, right? So it's something more than just the data itself, because the knowledge of the data is in the data, right? So for instance, in the context of the video, the knowledge, the data tells me what each individual person is doing, right? I don't need to put that into my domain knowledge. The domain knowledge has got a general principle, general common sense principle that says any event, whatever event that is, if it is true now, it's not true later, something has happened that has terminated it, right? And this is a completely general common sense principle, right? So it's not necessarily about describing what the data is, right? It's a general common sense knowledge. And of course, subsume a lot of millions of videos, right, where this particular knowledge is true, where this knowledge is false. But if I represent this symbolically in an abstract way for any kind of event, I can avoid all those data that normally a machine learning, which is only data-driven, will need to have in order to learn both the knowledge, the general knowledge, as well as solving the task of predicting an event.
Great. Thank you.
So I think I think it's either a comment or a question from Ping Wu saying that concept of domain knowledge sounds similar to the Bayesian approach, I think that so that the link into Bayesian statistics and the rest. I don't know
Yeah.
if you want to comment on that.
Yeah, I can comment on that. There are also a lot of work that that basically so if you have a probabilistic symbolic reasoning and in this context, there are a lot of work that compare Bayesian statistics, Bayesian inference with the probabilistic symbolic inference, right? So and there are lots of papers on that explore pro and cons or equivalencies in certain cases, how Bayesian inference can be captured in probabilistic sense in the context of logic-based knowledge representation. But what we actually do is like learning the structure of the Bayesian model, right? So, and then maybe on top of that, you can learn the probability functions, right? On top of the Bayesian model. So we see in the extension of this symbolic machine learning that combine probabilistic inference with not learning knowledge, domain knowledge, or the knowledge representation. It's I would say it's complementary a little bit to Bayesian inference, right? Because in Bayesian inference, you want to have the structure that Bayesian model kind of define, and then you work about the Bayesian statistically on the probabilistic part, right? On the parameterization of that. Whereas we can actually learn the structure part of that, right? And then if we do probabilistic extension of that, you can do a probabilistic inference on top of that structure that you actually learned, the model that you actually learned.
Great. So, here's another question. I was gonna stop us there, but we'll squeeze in another quick question from Darcy Murphy. How do you handle the risk of racial bias from using a feature like crime rating, which is influenced by the racial bias in policing? What do you do about bias, basically, is the question.
Yeah, okay. So there are two ways in which you can deal with bias, right? So one is you can actually analyze the data, right, in terms of bias. You can actually even learn whether there is bias in the data, right? So if you think about a certain kind of bias characteristics that you want to try to analyze, you can take the data, extract the features from the data, and then learn, general situations of bias, in which context the data are biased or not, right? And so that's something that can be applied, and not just to solve a task, a decision-making task, but where your decision-making is actually whether the data is biased or not. So you can come up with that kind of application of symbolic. We haven't done it, but it is actually doable. You can come up with an application of symbolic and machine learning, right? If the data are a little bit biased, in the context of the neurosymbolic I was describing before, where you take a prediction from a trained network, and the network's been trained on bias, all right? Then if it's trained on fully biased data, once you learn your model and you explain it, you are able to detect it, right? The human is be able to see what has been learned to make the decisions and understand the decisions, and generate an explanations for the outcome. And you can kind of understand what are the characteristics. So the human can actually audit that, all right? If the data is not just fully biased, but there are some good examples, the majority is biased, then what I showed before, that you can learn even from very few good examples, good features, even if the majority of features is not right, you can still learn a robust model. Then I think that would be another way of dealing with bias, right? So there are different directions.
Good. And I suspect we might touch on this again when we get to Honghan Wu's talk in the afternoon. So that's good. Mark, who has just materialized on the screen there, will be talking about exascale. We've covered in this bit of it, we've really covered, well, I think of it, you may think of this in different ways, but I think of it as one of the big disruptors in healthcare is AI, machine learning, and all of that. So we've been through a bit of that. But then there's another two to come. And Mark and exascale is one of the big, I say disruptors, these are big opportunities as well. And then Elam talking about quantum is another huge potential disruptor, a huge big change coming our way. Great, so we're back for the next one of our sessions, and the first talk is by Mark Parsons, who is probably the person who I would say knows most about exascale compute in the UK. And he's also actually been a real stalwart of HDR UK, and before that, the FAR network and all of this. So one of the few people who actually understand both sides of this equation. Over to you, Mark. Take it away, and we'll see where that goes.
Great, thanks very much, Dave. And thanks very much for inviting me to speak. So I'm going to talk about exascale computing. Can everybody see my slides okay? Is that fine? Yep.
Yep.
So I realize that this has not been a big area, supercomputing, for health medical research over the last 20 years in the UK, but I think we do have opportunities as we move into this new era of supercomputing. And so I want to give you a flavor of that, talk to you about what an exascale supercomputer is, and also show you some of the things that have been done, particularly in the USA, as they've already got an exascale supercomputer. So I need to start off this talk by explaining what a flop is, because I will talk all the time about flops, and if I don't do this, I'll be heavily criticized. So a flop is basically a calculation per second, so adding two numbers or multiplying two numbers. And we measure the speed of computers in flops. And so today in the UK, we're really in the petaflop age. We've got a 25 petaflop computer, but we're aiming for an exaflop. And a lot of this talk will focus on that. We measure this by using things called benchmark programs. Now, an exaflop is an awful lot of calculations. And if I was to give everybody on the planet a calculator and tell them to do one calculation a second for 12 hours a day, it would take all of humanity 8 years to do one exaflop. It's 125 million calculations per person. And the computer that we're going to have will do that in 1 second, just to give you an idea. So they're phenomenally powerful computational devices. But I often get asked, what makes a computer a supercomputer, or what makes a computer super? And the thing is, it's actually not a fixed thing. It's always partly the size, partly the performance, partly what you can afford at the time, and also partly the technologies that it's made from. But really, a supercomputer is just bigger, faster, better. And over the years, they've come in many different shapes and sizes. These pictures here are of two of the computers from the start of my career. The Mako CS1 is what I really started on. It did 800 million calculations a second. Archer 2, which I'll talk about a little more later on, does 25 million billion calculations. So over the course of my career to date, the computer that I use has got 31 million times faster. And there are very few areas of science or our daily lives where these sort of changes have happened. And of course, they influence all the way down to our personal lives as well, with mobile phones and the games consoles or whatever we have in our houses. And interesting, the technologies we build supercomputers from today are the same technologies that are in these things that we have in our homes and our offices as well. So I show this slide to show you this progression of systems over time. And you see in the beginning that the large systems we had were quite small, 64 processors, 16 processors. And through the 90s, they grow until, by the end of HPCX, which was one of the big successful HPC systems we had in the UK, it had 1,600 processors. And then we go into this multi-core age where QCDOC had 14,000, Hector by the end at 90,000, and then we're into the modern age of what we think of as supercomputing, very high core counts. So Archer at 120,000, and Archer 2 has got 750,000. These are really big, complex computational devices. Archer is interesting because it is the current national supercomputer, but it's actually now quite old technology, in as much as where we've gone with supercomputing over the last 3 or 4 years is to bring these accelerators in called graphical processor units, or GPUs. And we've all heard about GPUs because of AI, et cetera, et cetera. So Archer does, its peak performance is 25 petaflops. Its measured performance is 19.5 petaflops, so 19.5 million billion calculations a second. But an exaflop is going to take us all the way up to 1,000 million billion, sorry, a billion calculations a second. Need to get my billions correct, which is 50 times more powerful. But we shouldn't forget, where we are today with Archer 2. Archer 2 is absolutely full of science. It's consistently the most busy system that we've ever operated. Its allocation and its usage is consistently above 93%. And in the bottom right-hand corner here, you can see this big wedge of purple. That actually is Archer 2 running on Christmas Day. And the tiny sliver of grey is unused space on Archer. The pink and the green are allocated and reserved. We've also spent a lot of time with Archer 2 really understanding how it works. And when we first got it, you can see here, it was using about 3.5 megawatts of power. We changed the way that it responds to the end of a job about 6 months after we got it, and we started saving 300 kilowatts of power. And then we slowed it down a little bit about another 6 months later from 2.2 gigahertz to 2 gigahertz. And we saved quite a lot of power that time. And in total, just by making these savings, which haven't actually affected the speed of the system very much, less than 1%, we've saved £1.5 million of EPSRC's electricity bill, which makes EPSRC very happy. And obviously the environment too. Just so that we're all on the same page with regard to parallel computing and supercomputing, I thought I'd do my parallel computer in one slide. So if you think of a problem, think of a two-dimensional problem. In the early days of supercomputing, we built vector computers, and they just tried to solve all of this problem, all of this matrix or whatever it is, on one processor. What we discovered very quickly was we couldn't make processors, single process, faster and faster. So we started cutting the problem up into pieces and handing it to individual computers or servers or nodes, we actually call them in supercomputing. And these servers have to communicate with each other because, particularly at the edges of these bits of data, you've got to save the changes you've made to the next processor. So for efficient supercomputing, you need really high speed communication between the processors. And of course, in a modern supercomputer, you break these problems up into very large numbers. And Archer 2, the largest granularity would be 750,000 cores all working at once. We tend to think of nodes, but even then, Archer 2 is 5,860 nodes. So you've got a big and very complex network where they're all talking to each other. So exascale is the current frontier. I say current because we do now have exascale supercomputers in the world. And, as I said at the start, supercomputing advances by setting itself targets. Exascale at some level isn't important per se, but it's a target onto which you can hang a case for why we need this for science. And this is what's happened in Europe, in the US, Japan, and the UK. It takes a long time to make these cases. I started working on exascale for the UK in about 2010, properly working with the government about 2018, and we've still not even begun the procurement, although we are moving forward. So as I said earlier on, Archer 2 is 50 times less powerful than exascale. So this is a big leap forward. But interestingly, exascale will have 6,000 nodes. So that's virtually the same number of servers as Archer 2. So these GPUs, these accelerators, are basically where all this additional computational power is coming from. And that does mean it's going to make these computers slightly more difficult to program, because you've got to worry about feeding the accelerators with enough data so that we can realize the computational power that they actually provide. And the first exascale system in the world was the US's Frontier system in 2022. Here's the Cray-EX system, which is about the same type of system as Archer 2, but instead of just having cores in its nodes, it's also got GPUs. So it's got an AMD processor, which controls 4 of these MI 250 GPUs. It's got a similar network to what we have. We've got Slingshot 10, they've got Slingshot 11. And just before the International Supercomputing meeting in 2022, a few days before, they managed to get it to work continuously for 4 hours so that they could produce this benchmark measurement of it. So just 1.19 exaflops per second on, and this is where I find it quite amazing, 37,888 GPUs. These are really, really massive computational resources, and also look at the number at the bottom there, they also consume an awful lot of power. So 22.7 megawatts is what Frontier consumed while it was running that benchmark. Interestingly, I went to a talk a few years ago when we were talking about what exascale might be able to do. And there was a general agreement in the room that it probably is powerful enough to simulate all of the neurons in a cat brain. But somebody did point out, at the time we were targeting 25 megawatts for exascale computers, somebody pointed out that a cat brain uses less than 25 watts. And there's clearly something we fundamentally don't understand about the brain and its relationship to computing even today. The majority of supercomputing focuses on modeling and simulation, and there is crossover to AI, and later on in this talk I'll do that. I'll talk about that. But these are typical of the simulations we're running in Archer 2 today. In the top left-hand corner, that's actually modeling of part of the COVID virus done during the COVID pandemic. Bottom left-hand is something that we do lots of in the UK. We're particularly expert in the modeling of turbulence and shockwaves, etc. Bottom right-hand, from the National Oceanography Centre, it's part of the NERC community that are big users of Archer 2. This is them modelling the creation and regression of sea ice annually in the Northern Atlantic to understand in particular the heating and cooling of water in the North Atlantic. And top right is a project that I run, which is for the first time we're trying to produce a full working model of a Rolls-Royce gas turbine engine. I'll talk a little bit more about that as we go along. So, oops, let's see if I can move on from here. There we go. So some of you have been aware that the government has been thinking quite hard about this over the last 3 years, I would say. Initially, the Government Office Science published a report on large-scale computing. And then the current Prime Minister, when he was Chancellor, set up the Future of Compute Review, where he got a chap called Zubair Gharami, who's a Professor of AI at Cambridge and also the Google DeepMind Professor of AI, to chair an independent panel that looked at large-scale computing, both at exascale and at AI. And it made 10 recommendations, which are really split into 3 themes. One, which I think is probably the most important, is to have a long-term rolling 10-year strategy. Other countries do this. It's happened in Europe through EuroHPC. It happens in Japan very well. It happens in the US. And for some reason, the UK has never really done this. And hopefully, this is well, it certainly is the direction of travel we are on now. It's not quite in place yet, but we are going to have this 10-year rolling strategy from now on. The bit that caught everybody's eye, of course, was the announcement of an exascale system for the UK, and also this program of other systems which are called the AI Research Resource Systems, 2 of which have already been announced, and others are in the pipeline at the moment. And then I'll come back to the exascale plan, but the plan as announced was 250 petaflops by 2024 and an exaflop by 2026. And the final point was to invest in software and skills. So really think about, it's not just about buying computers, but making sure that we've got the skills to use that computer, to write the programs, to think about how we express the science we want to do in the algorithms that we're implementing. The UK government's actually been quite clear about the requirements that it wants for the exascale system. So the system is kind of a twofold system. It needs to support traditional modeling and simulation, but it should also be able to do large-scale AI or deep learning applications. And if you said that, even 3 or 4 years ago, that really would have impacted the sort of computer you were going to build. But because processor technologies have moved on and it's become extremely common to have supercomputers with GPUs in them, I think there's this big blurring of the distinction between a supercomputer and a supercomputer designed for AI. I'll come back later on and talk a little bit about why supercomputers can do AI, but they're not necessarily the way that users want to have their AI computing presented to them. And I think this is something that's actually quite a difficult thing to get right. The other thing is that the system will support both scientific user communities and industry users. And 20% of the system is going to be ring-fenced for industry projects. And I think there are real opportunities here in the health and biomedicine space for more industrial engagement in the use of the UK's research supercomputers. I'm very positive about this, and also support for small companies too. The original plan was to install the 250 petaflop system in 2024, but that's impossible now because the procurement hasn't been opened yet. But there's a lot of work going on behind the scenes, and decisions will be made soon about exactly what will be procured and its scale over the next year. So you have to set certain design parameters when creating big systems like this. And one of the parameters we set from the start was the system should consume no more than 25 megawatts of electricity, which is an enormous amount. If you think the UK at the moment is probably consuming about 25 gigawatts of electricity, you can think of an exascale system consuming around 0.1% of all the power in the UK. So it's a significant amount of power. We're targeting a full exaflop, sustained exaflop, so the computer can actually do it. And the idea all along has been for it to be accompanied by an Archer 2, so that we have a stepping stone from a CPU-only resource to an accelerated resource, and also that it should have a large application software program. And most importantly, it's the first national high-performance computing service for all UKRI research councils and researchers. I've never really understood why the HPC services, the large-scale ones, were linked specifically to research councils. So the DRX systems have been linked to STFC, National HPC has been linked to EPSRC and NERC. And as a result, I think we've seen too little collaboration between different areas of science in the UK. So I'm extremely happy that this system will be for all of UKRI. I argue very strongly for that. So just to give you an idea of the sort of processors that the system will have, it will, as I said, be made from 6,000 nodes. Each node will have 4 GPUs. And basically the only two options at this point are either NVIDIA's Grace Hopper super chips, that's an ARM chip plus one of their Hopper GPUs, or AMD's new chip, which has just come onto the market called the MI300, which is a very large GPU, which has got 24 cores, if I remember rightly, on the GPU. So it's a single chip that does it all, whereas the NVIDIA one is 2 pieces of silicon effectively glued together. And we're expecting our system, when it's running at full whack on the benchmark program in particular, to use about 22 megawatts and around 15 or 16 megawatts in normal operation. I was considering whether or not to show this slide, and I want to because it explains the difference between an exascale server node and an AI system a bit. So in an exascale server node, you've got these 4 CPU modules, and that's either the NVIDIA or the AMD option. And they talk to each other on an extremely fast internal network, a very clever network. And each of them has got a network link to the network that joins all the nodes together. And in an exascale computer, to date, they've all got four network links, and they're very fast. Ours will either be 200 or 400 gigabits per second. And then the really, really important thing about this is, for the very, very first time, any of the processors can see data anywhere on the node. So we call it a single address space shared memory. So it's completely shared. In the past, you, the programmer, have had to think about how you move data into the GPU from the CPU it's attached to. All that goes away at exascale. And this is the key technology difference. In the AI world, this is not a ridiculous system to do AI on, but it is different from the traditional way that systems have been presented to the AI community, where you much more used a single CPU or maybe 2 with 8 GPUs. And I put together this slide a couple of weeks ago to sort of talk about the difference in AI systems and exascale systems. So, both are built from CPUs and GPUs. Quite often nowadays, you have multiple servers networked together, particularly for people that are doing large language models and things like this. The GPUs are almost identical. Both have CPUs, but use them differently. And they can both run similar workloads. You could happily do some supercomputing modeling and simulation on an AI system and vice versa. And certainly for large-scale AI and exascale, they have similar data needs. But there are differences. So most AI projects use a single 8-way GPU server, as I said. The largest AI problems today scale to around 3,000 to 4,000 GPUs. After that, you don't get any improvement in performance by adding more GPUs. And to be honest, certainly at Edinburgh, a large user today is using a single 8-way GPU server. Many users are just using one GPU. But an exascale system, our one's going to have about 24,000 GPUs in it. So I think it will be used at times for large AI training problems, but it's certainly not going to be its main focus. Its main focus will be on modeling simulation. I think AI servers are run differently. They tend to be virtualized. They tend to be containerized in a very rich software environment. Exascales are more traditional software environments. So 50% of the UK's modeling and simulation software is written in Fortran, for example. And the way to think about it is, in exascale, the CPU takes part in the calculation with the GPUs, but in AI, I think of the CPU as the conductor of the orchestra. All of the work's really being done with the GPUs. The CPU's just marshalling them. And exascale tends to have a more expensive, complex network between the servers. But the key here is to understand that you can do both on each or either. So I don't want to labor these next few slides, but we've put a lot of time and effort at Edinburgh into preparing the environment. Just show you some slides of Computer Room 4, which is where it's going to go. In 2023, the government announced that we will be hosting the exascale supercomputer, so we're making the preparations at the moment. We've spent just over £30 million so far in the room, but that's involved adding a 30 megawatt power supply, which for anybody that lives in Edinburgh, I apologise for digging up the road past IKEA for 6 months. So we've now got in total 38 megawatts to site, actually in dual supply. So theoretically, we've got 76 megawatts to site, but we only use half of that at any one time. This is the room itself. And this is the power and cooling, but at the moment, this room is only set up to distribute 6 megawatts of power and cool 6 megawatts of computer, but you can see the infrastructure here is enormous. On the roof as well, these are very similar to what we will be adding for exascale. But again, this is just for 6 megawatts. So what we're doing at the moment is just beginning a extension project to Computer Room 4. So the current computer room I showed you in those pictures, the top here, the actual room itself, at the bottom is the plant room where all the pipes and the other things were for electrical distribution. This red dotted line is the current building. So we're extending the building with all this bit at the back, which is just for power distribution and cooling distribution. And we're slightly extending the computer room to make it easier for us to install the system. But in fact, an exascale system would fit in the current room if we wanted. If we do a split system, then that blue area is where the 250 petaflop system will go, and the green area will be where the remaining 750 gets added later on, and the yellow bit's literally is just where the water comes from. So I wanted to talk a little bit now about some of the things that have been happening in the US around with these big systems, and particularly with thinking about health and medicine. And all of these examples come from papers at the Supercomputing Conference. It's just the big conference I go there every year, I know it very well. So this is a paper from a couple of years ago by Andrew Blanchard at Oak Ridge, and I put the links to all these papers on these slides. They basically trained, they took a pre-trained BERT model, which they trained on a data set of 9.6 billion molecules. So one of these big data sets that has the shape and the, what is actually in the molecule, the atoms in the molecule. And then they used Summit, which is the previous American national supercomputer, to help them predict molecules that would bind in particular ways with the SARS-CoV-2 virus and inhibit its reproduction. Very, very interesting paper. And you know, this is really one of the first papers to use a language model to look at this stuff. It's becoming much more commonplace, but this is from, I think the work was done, it's published 22, it was done in 2020. This is a very beautiful paper, again, one of the COVID ones from the Gordon Bell Prize, which looked at how the very carefully modeled using multi-scale computational microscopy, again, the SARS-CoV-2 virus, but in a respiratory aerosol, to think about how it was being expelled and also then ingested into the lungs by people who are sneezing, etc., etc. It's a very beautiful paper and lots of nice pictures in it. This is a paper that had a number of, this next paper is a cryo-EM paper, which had a couple of the real experts in cryo-EM from the UK, particularly Professor Sarah Harris. And here they were looking at how the COVID virus's replication transcription machinery worked, and they properly modelled how RNA unwinds during this process. It's a very, very interesting paper. I have to say, it's true of all these papers. I don't understand the medicine behind them, the biology behind them, but from a computational point of view, these are really, really impressive pieces of computational science. And then finally, I think one of my all-time favorite papers, because it transformed public health policy in Japan and globally. A very junior or reasonably junior member of staff at the Riken Supercomputing Center took a code he was using to model combustion, and particularly the spray of fuel inside an internal combustion engine. And he decided himself to turn it overnight into modeling a sneeze. And the spray of fuel in fuel droplets in an engine, it turns out, can easily be turned into somebody sneezing. So he did that, and then they have models of Tokyo, or 3D models of pretty much every building, because they do lots of optimization around the city to make the city cooler during the summer. And he took all of these models and he started modeling people sneezing in these environments, both with a mask on and without a mask on. And him and the team, they used a huge amount of time on Japan's national supercomputer, Fugaku. And they did all of these different types of simulation in cars, in hospitals, in lecture theatres. And it was this paper that convinced the Japanese government to mandate masks very early, but also the Japanese government say is the reason they didn't lock down. And if you look at the result of that today, is Japan had fewer economic problems and no higher mortality rate than we had in the UK and elsewhere in Europe. So a very, very important paper, and just a fantastic piece of work if you really if you look into it. So final slide for me is a little bit more about the engine modeling that we're doing. So if you look at the picture on the right, the thing we really are able to model today is right at the heart, is the turbine at the heart of that whole engine. And what we want to do with my Asimov project is model these whole engines in their entirety. And to do that, we need an X-scale computer. And we've been working on, for the past 5 years, on this new engine model. And it's going to take another 5 years to get it fully in operation. But at the end, we'll be able to do full digital twins of these engines and actually stop having to destroy engines, do destructive engine testing on them. We'll be able to do digital testing of them. But during this, I've learned about much more about how Rolls-Royce in particular have used modeling simulation to improve the energy efficiency of their modern extra wide body engines, their XWBs. And purely through modeling simulation, they've saved 15% of the fuel, made them 50% more fuel efficient over the last couple of decades in total. That equates to an annual fuel saving per aircraft of around 15,000 tons of CO2 that have 2 of these engines in operation. Exascale will only generate around 41,000 tons of CO2 per annum through the electricity it uses. So 3 planes powered by these Rolls-Royce engines will save more than all the CO2 that Exascale will generate, purely thanks to the modelling and simulation that's been done on UK supercomputers. So while I have to explain about Exascale and its power usage a lot, we need to bear in mind that modelling and simulation actually is a way of cutting down hugely our the CO2 that we're pumping into the atmosphere today. Thank you very much.
Great, thanks, Mark. If we can go back to perfect, back to the normal screen view. And usual drill, people who want to put questions in the chat or raise your hand while people are thinking about. Oh, I was going to ask one, but somebody's got in. Marcos Barreto says, any movements towards quantum computers or a mixture of exascale and quantum computers at the center? I'm not quite sure what that means. Marcus, you might want to ask that question because I'm not quite sure what it means.
No, I do know what that means.
Oh, okay, you know what it means. Oh, that's good. Somebody does. So
our next speaker, Ellen, will be much better answering this, but I'll have a go and she can tell me whether I'm right or wrong later. I think at the moment we do see quantum computers as operating with supercomputers in a sort of accelerator way, so that we will attach quantum computers to high-performance computers, maybe not exascale systems. There's a lot of work to be done at the moment to allow quantum computers to work at pace with a supercomputer. But there are problems you can do in quantum computers that you simply cannot model or do in a timely way using traditional supercomputers. So yes, I do think we will have them. There's a huge amount of modeling of quantum computers going on supercomputers today because we can't build large enough quantum computers. So I think there's a very nice complementarity between the quantum computing research area and the supercomputing area at the moment.
Good. Okay, so well, here's a curly one from James Rafferty. He says, do you have any thoughts about how to leverage cutting-edge computational infrastructure and sensitive data sets that are often stored in trusted research environments? I bet you do.
So we've talked about this a lot. We have a way of pivoting one of our modest supercomputers into and out of our trusted research environment. People want to use it. But in terms of using the really large scale computers like Archer 2 or the future exascale system, the area where we've solved that is not with personal data, but with confidential company data. So we have ways of encrypting that until it's only decrypted once it's in the memory of the supercomputer, and then the node is completely wiped at the end of it. So it never leaves, any results are written back in an encrypted way to the disk. And we've got that in operation now. It's passed all the security requirements. I think we are a long way from getting permission to do that with medical data, if I'm completely honest. But in truth, it would be more catastrophic for the engineering data to be lost than the medical data, I think. It's just because it's personal data, people are much more paranoid about it. And I do understand that.
One from Darcy Murphy, an energy-related one. Do you have any idea of the difference in CO2 produced by running simulations on supercomputers versus more slowly on smaller computers? I'm guessing there's an energy savings from operating at scale. Don't know if you have any quantification of that.
So that is a very good question. There's been a lot of work done in how, if we make a code run 20% slower, how much power do we save, and does that make sense? That you have to offset it against the carbon that you've expended creating the supercomputer in the first place. It's non-trivial discussion. The one thing I would say is that in going from an Archer 2 node to exascale node, per flop, we're using 10 times less power. That's the big thing, because if you try to build a, if you try to increase Archer 2 to do an exaflop, you would need 200 megawatts of power. So we know simply that by supercomputing, pushing the boundaries of what you can compute on a bit of silicon, we're already saving a huge amount of energy just in itself.
Okay, so next, I have another question in from David Cameron, the famous one, the oncologist, not the foreign secretary. He's saying, if the increase in computer power is achieved with more and more processors working in parallel, does that give you more opportunities to formulate different types of questions or open up new questions we could ask in medicine? For example, Monte Carlo simulations run in parallel and their outputs all competing to win, to influence the final model output. This is a really important question, because one of the things that these systems do is change how you view your science. Could it change that sort of thing?
So that is an excellent question. And I have had the horror of explaining to government ministers that it's more complicated than that. So if you look at Archer 2 and its predecessor Archer and now going to exascale, we only have around 6,000 servers in each. So the big change between exascale and Archer 2 is simply the computational performance. There is a little change in the amount of memory we have per node. So each node in Archer 2 has got 256 gigabytes of RAM, and exascale will have around 512 gigabytes of RAM. So if you think of the size of problems we can do, we can, depending on the shape of things, double the complexity of the problem we're solving. But we can't make it 50 times more complex because we'll run out of memory. So we will be able to do things more quickly and more of them with exascale. We will be able to do more complex things, but not 50 times, just by a factor of 2 or less, in fact, when you go to 3 dimensions and stuff like this complexity. But I had to explain that to government minister in this odyssey that I've been in. It was interesting.
Good. So another question from Darren Gates, who says, presumably farming the data and problems for quantum and supercomputers is quite different. Are supercomputers going to be more suitable for real-time inference?
It's very interesting. I attended a talk the other day from a group in the Netherlands who are doing an optical computer for inference. And it will use tiny amounts of power. And the idea is that they can do inference out in the wild, so sort of an Internet of Things type device. And the reason they can do this is because once you've trained your model and you're just doing the inference part and you're not going to update the model, you can do really quite interesting things. I have not thought about this in the quantum context at all, I have to say. But people are definitely thinking about it in the photonics context, and the people that are doing optical computers, they're really thinking hard about real-time inference and optical computing, which is a surprise to me. I wasn't aware of that until this talk last week.
Okay, I'm looking to see if there are more questions in the no more questions in the chat. Any more hands up? I have the luxury of one question. There's a tiny bit of time. This is a very broad strategic question, but you may not know the answer. So there's a bit of lead time now before we get through to something approaching exascale. And some things have been done on supercomputers. You put some of those in your slides, but not so many, maybe, compared to physics or whatever. How do people are enthusiastic in healthcare and medicine? How do they get, because it's a crowded landscape, you showed the picture of Archer, how much it's utilized. How do they get to the front of the queues for these kinds of things?
So one important change to the tier 2 systems, high performance computing systems that EPSSC have funded, is that anybody can apply for time on from any research council. And that's not happened with Archer 2 yet, I think largely because it's so full, but certainly for the tier 2s, anybody can apply. In parallel, though, we've got the first AIRR systems coming online. So there's the system at Bristol University and the system at Cambridge University. I think the Bristol system is going to be online by the end of this summer, and I think the Cambridge one's coming up at the moment. People will be able to apply for time on that. So if you're doing a health data HDR type projects, like some of the ones I showed, particularly BERT models and things like that, you will be able to get time on those systems to do that. You won't just be able to do traditional supercomputing type work, but certainly you'll be able to do AI and health type work. And it will be interesting to see what sort of data and how they manage the data for projects that, even if it's consented data, they'll need to think about how they manage that properly, I have to say.
Okay, so I see no more questions and timing is nearly perfect. So we now move on to Ellen and quantum computation. And folk from healthcare, I don't think have had so much exposure to quantum computation, but has the potential to be truly disruptive. But I'll leave that for you to explain, Ellen. Take it away.
Thank you so much, Dave, for the invitation. And thank you particularly for putting me right after Mark, so I can say that, yes, indeed, we're going to do everything that Mark told you, just bigger and cooler. So, but with the slight subtlety that Mark has his devices already being installed, whereas my machine is still in making. So I'm hoping to take you through that journey. They're exactly telling you where we're going, what we're going, and we are doing everything just to answer to one of the questions. Indeed, we are learning a lot from our colleague at EPCC, and all the pain points. So let's go through it. Let me set the agenda and tell you what I want to tell you. So quantum data machine. So let's see. You see my next slide, I'm hoping. So by now, I guess everybody convinced after this magnificent talk by Mark that we are all building this big data machine. Everybody trying to collect more data, to correlate more data, to communicate more data, to trade more data. So, essentially data and computing is the new commodity. And the two questions that was also raised during the discussion, not just in case of the healthcare in general, that how do we secure this data and how do we address the tough question, especially in the healthcare regarding data sharing, because everything in the new world is about distributed computing versus regulation. So what do we do with this big data machine? As if it's exascale of Mark is not enough, we try to put blockchain on top of that. And that's what trying to address some of this question. We're trying to build large language model on top of these things in order to address this big data machine. And in short, I guess everybody in this community agree that this fast, massive, secure, accurate data machine will consume the energy of the planet. So to me, as I know, already you guys yourself are very disruptive, and we need to really try to address this big challenge in front of us. And surprise to surprise, in order to break that barrier, we need completely new tools coming to our case. So here's a slide that I'm going to do my 101 quantum computing for you in order just to say how we are changing. The quantum is not just the extra scale quantum classical machine, is really thinking differently about information, thinking differently about the very nature of computation. And again, referring to some of the very nice questions, it comes thinking differently about the whole mathematical problem. So what do we do in the classical computer? We have our 0, 1, the classical bits, we like them. We measure, we observe them, we reveal the value of those bits. They can be copied and they can string put together and they can describe locally. This is exactly what you teach to all the children, which is wrong because we need to teach them, in fact, qubit can exist simultaneously in the states of 0 and 1. That's for you massive parallelism by design. Measurement will change the value of your central bits information qubit. But when you measure a qubit, you actually change its value. The value, the information that has been encoded in our qubit, equivalent of bit, actually cannot be copied. And when you put this string of this qubit next to each other, they create non-local correlation. So what I listed in here are the things that for the last 100 years have bothered physicists, you know, from Einstein, who actually hated quantum mechanics, all the way to all the people who are trying to understand. These are bugs, you know, in a sense. And that's the beautiful of computer science, because we took all those bugs and we turned them to features. For us, the fact that such a thing exists that cannot be copied, that we have different type of correlation, our measurement changing, I would hopefully in this short talk can show that all those elements allow us to break the barrier that I was talking about. Okay, so it's a big claim. I try to give you bits of pieces of it, but in short, if we look at the quantum computer, and I will walk you through a little bit what is quantum computer, how is it going, where we are, is essentially it's giving a different notion of speed. Let's hang for a second and use borrow from Mark. Mark was talking about the flops, and he was talking about this amazing power that the exascale computation will have. So in comparison number, actually, I learned this thing from Mark's team, that when we have the exascale computer established, it has the capacity of 45 qubit machine. So already Archer 2, when you simulate it and put it there, it has the capacity of 40 qubit machine. We are talking about building machine with 1000 qubit. So I want you to start, you know, not even writing the flops number in here. Once we have those devices, we have entered a different regime of talking about speed. And already in order to teaser, indeed, we're thinking about inferences very, very differently. So that's about the speed that this machine will bring for us, as well as security. I mean, all those bugs when I was saying, oh, you cannot copy, you cannot change, those are elements that allow us to think about security and privacy and integrity in a completely new way, in a completely different way. Again, I'm hoping that I can showcase you example that is not anymore post hoc at our core of our element, because we are changing rather than mathematical encryption with this physical encryption. And in short, again, putting all of this together, there is this beautiful program called Quantum Energy Initiative, which calculating very carefully, comparing to the exascale, to the various machines that are emerging, that how the energy of this machine are going to be much lower cost. You know, maybe we have the magical cat of Mark, you know, it's just going to be Schrödinger cat that indeed is working with a much lower energy. So these are the buzzwords. These are the things that we're trying to achieve and breaking those barriers. And in short, if there is one thing that I want to say for our future, you know, we strongly believe this future, secure, fast network quantum data machine can deliver for public good. You know, where it is net zero, health, fraud detection. These are all the things that buzzword that we also need to tell to minister to make sure that it doesn't forget about quantum national program. But we believe, I think for me, the most important thing is avoid the hype, just saying that we have new tools to think, okay? We still, you know, 10 years, 20 years, 30 years, whatever magical numbers ahead. But we have been given a completely different model to talk about information. And I just want to tell you a little bit about what do we do with these tools. Okay, so that's the agenda. So is the world serious about it? Yes, it's very, very serious about it. You know, this is one of the many slides that you can see, but I think it's one of the latest one that is just looking at the various national government as well as the VC investment in this global quantum soup that is emerging, and is interestingly is pretty global. It's going all over the world. And in particular in UK, very similar to the strategy mission that Mark was showing you about compute, we have only less than a few months ago that we had National Quantum Strategy Mission be announced. Mark and I both working on the computing group, working group. But it's a very, very interesting, because in fact in UK, we have had 10 years of National Quantum Technology Program that has been running. And I mentioned something more about it and where we are with that. But in fact, futuristically, for the next 10 years, we have been dedicated 2.5 billion. Let's see if it's real money, and trying to make sure that we deliver collectively as a nation, these 5 missions. And I highlighted a few words because mission 1 is astonishing statement. Every time I'm saying it, I have a shiver in my skin, is that by 2035, in 10 years time, we will have a UK-based quantum computer capable of running 1 trillion operation and supporting application that provides benefit well in excess of classical supercomputer. So we have to beat Mark. That's what government wants us to do, which is a hard job, across key sector of economy. And one of those key sector, when you look at all the details, is healthcare. The mission 2 is also very, very interesting in terms of the privacy, because again, by 2035, the UK will have deployed the world's most advanced quantum network. They're exactly the same classical network that Mark was talking about, that how he needs to bits and pieces of a module together. We're going to have quantum network among all of those. And exactly that will provide, I hated the word quantum internet, but it's about secure privacy by design. And another mission that usually we don't work on it because it's go with the very physicky, but is essential is there is a dedicated mission that every NHS trust will benefit from quantum sensing enabled solution, helping those with illnesses, live healthcare. So these are very, very clear, ambitious and dedicated program, bringing the entire sector all together. And what I want to tell you, it's like we are not in any doubt that the only way that we can unlock this quantum utopia that we are all been working on for over the decade is to really have an ecosystem and lots of research. This has been always our job, to continuously reminding the policymaker that without research, we are not going to make it there. So I want to tell you a little bit about how we do it in Edinburgh and at the National Quantum Computing Centre. We are trying to really benefit from, and I guess this is my main message in terms of what's happening in the quantum, that we're trying to still bring the discovery in the science. It's still, we are on the frontier of science. Science is not done by no means. We're still surprising ourselves every day. But technology implementation is really happening. These devices have taken us to aware that, we are no longer Star Trek. We're actually reaching to be able to implement things. And at the same time, the need from use case, the need and pain point from the use case, that they are asking, what are the new tools? What can we do with them? And this cycle that particularly is the mission of National Quantum Computing Centre and the Quantum Software Lab that we launched at University of Edinburgh. We're trying to be an engine for this holy triangle of, science, technology, and use case. And the only way to go forward at this moment is to really be exploring all platforms, because there is many gadgets are popping out. We are exposed to all discovery, and really true quantum advantage, because there's lots of claims coming, but I like what we put in the mission. We need to really saying it how we are beating exascale. Otherwise, there is no point to have quantum computers. So I think finding this true quantum advantage are truly important. So let me briefly saying you what is NQCC. It's essentially because asking for opportunity for further collaboration as a follow-up, and in the discussion we can go through it. So it's a dedicated program that is launched almost 5 years ago, is joint between EPSRC and STFC. And the target, the pillar is just technology readiness, indeed delivering this UK national infrastructure for access to the quantum devices, as well as infrastructure readiness, or we call it quantum readiness, making sure that everybody understands what's happening in the quantum, how we can work for it, and how we can also do the scaling, the skill, through the hackathon, through the doctoral training center, which one of them is going to be open at University of Edinburgh, totally dedicated to quantum software. But in general, like any other national lab that we have, the target of NQCC has been to provide assurance, catalyze supply chain, focus development, enhance the skill, accelerate scaling, drive user adaptation. And, they are pretty much on row, and there would be the building which is opening in the next few months. And it's very exciting to see how far we want to go. Now I'm going to drag this a little bit toward to my own domain, which is more kind of application side of how we're going to use, but bear with me till I walk you through. One of the most exciting things that's happened just 2 weeks ago is that the SBRI overview was announced, and the NQCC has started acquiring their testbed. So seven different type of modality, because I didn't tell you what is qubit, what is quantum computer, but there's any system that can demonstrate this at macroscopic level, those bug that I was telling you, superposition of a state, quantum correlation, not copying, anything that takes us to the quantum mechanical level of description of the system can be potentially a quantum computer. And there are many platforms being explored. There is an atomic platform, there is photonic, there is ion trap as diamond, and superconducting. And what is so unique about this NQCC SBRI testbed is that for the first time, I think in the world, we have a collocation of so many different systems, and as we call it, the Lego pieces, the toys come together. So they are not necessarily the world's most advanced quantum computer, that that's around, but they are, as you wish, to some extent, in a white box that allows people like us, application and use case, to really go and try to, well, not really break them, but play with them. So this is something that I would highly recommend to have an eye on what will come. It just launched. They start establishing and building the system from scratch at NQCC, and we'll see what kind of application they will explore. And in fact, parallel to that testbed and hardware that is going to be installed at NQCC, we're also leading application program. The Spark program is probably many of the colleagues, maybe even I have been working it, is the way that the NQCC is trying to answer the question of, should I be worried about quantum? What does it mean quantum? When, how? These are my pain points. This is my question. Where do I bring access to the hardware, expert on the algorithm, and actually pain point of my use case to go through? And if you look at this thing, energy sector, healthcare, using machine learning optimization, pharmaceutical, there are several projects that have been running in the first round of the Spark. And I think the most recent one, and again, they have been launched in the logistic, in the aviation, in the material discovery, etc., finance, obviously. And so all of these things are beginning of the triangle that I was telling you. So we're bringing use case, very concrete pain point coming from the end user. We're bringing access to the hardware to give us a realistic understanding of the performance and structure that we have. And we're bringing the scientists and researchers to really trying to scratch their head. Okay, how do I go about this thing? So it's a very, very rich ecosystem, and I'm super excited to see what will come out of it in terms of, if you like, the early discovery stage. So now what I want to do, I just want to, with the hope of just to give you a feeling of how these tools are coming together, and why do I insist it's really an ecosystem. It's a giant effort that we have done it in the past when we had something like EPCC who bring the end user, the hardware, accelerator, etc. And exactly what Mark was showing you is that how we're going to do exactly the same in the quantum, and what does it mean? So we have just launched this program. It's called Quantum Advantage Pathfinder. As one of the co-founders is also from EPCC. And what we're trying to do as computer scientists, as an application, as a hacker of this magical device, is that we are ready to start talking to our industry pain point, to understand exactly what are the things that currently might not work with the classical means. And then we try to drag it back to the lab, this reverse pitch, try to understand this thing to become a mathematical problem and translate it to the quantum algorithm, and then using the testbed and all these access devices that we are telling you to start implementing and benchmarking, because there's lots of things. I say that our devices are still being built. We're still interpolating at what will come in the next decade, and trying to answer the question as this trusted authority, if you wish, that is there going to be any quantum advantage or not? So because the mistake that many people might say is that once we have the magical box, it's going to solve all of our problems. No, there are many, many, many problems that remain specific, useful, and even not necessarily extra-scale computer advanced. We know it. There is plenty of problem that classical computer can do. We need to figure out when the exascale computing is useful, and we need to again find the niche area when the quantum platform is useful. And that's what we want to try to do at Quantum Software Lab, to answer that magical question, to quantum or not to quantum. So I thought I'd put a use case. I'm just walking through a little bit of the technical paper, but it's not really technical. I just want to tell you the story. For me, it's more interesting to tell you the story of how we are bringing various bits and parts of this Lego together. And in fact, is example from quantum generative AI inferences as a case study that we have been working for a long time. And the initial goal is just essentially enhancing the understanding of system correlation and higher order interaction. If I pose in here, if you remember, Feynman was one of the people that originally even asked why quantum computers shouldn't exist, because he was saying, simulating nature is damn difficult, and deal with it, and how beautiful it would be if we build a quantum system to naturally simulate that. So that was the very beginning of the idea, and it's still one of the core applications of quantum, that indeed, if we have quantum a many-body system interaction, the best way to understand it is just using the quantum system. But what we are start learning through this thing is that when it's come to the data, despite the fact that this data might be classical data, through our quantum generating AI, we are accessing different way of correlation. And we are not completely understanding this ourselves, the same way that we don't even understand what AI is doing it to begin with. So just add a bit of soup on top, it's just become completely uninterpretable. But it's just really walking in the different space that allow us to come up with a different way of looking at AI. So when we start working in this framework with Standard Charter, Rigetti, and etc., it was in the case of synthetic data for fintech, but in particular, it's applicable to any other scenario, as I will show you. And the two pain points that become very, very immediately interesting is that, well, we want to have more private data. We want to bring privacy in this whole generative AI. You know, not everybody is willing to give you their data so that you can do whatever you want to do to create the synthetic data. There is a clear issue when you want to bring the privacy. And sometimes it's not just about the speed of creating your data, synthetic data. It's more about accuracy. Can I get actually a better notion of accuracy of synthetic data? So going through our, quantum advantage pathfinder, we realize these are two different problems. What quantum machine learning can do for here and what differential privacy can do. And each one of them, the reason I'm presenting this thing, because they are classical method that we are using in the quantum setting. So it's not like we are reinventing the wheel. There is a lot that we're saying. We're always saying AI for quantum, quantum for AI. Hence my title is really we're trying to see everything that has been done in classical setting and see when it can be used in quantum. And at the end, I'm going to pitch to show that how this thing actually turned to a product, if you want some prototype for privacy preserving quantum machine learning in the cloud. So let's start. So essentially, yes, we already heard amazing talk before, which is all about retrieving interaction in complex systems. This is our what bottleneck, and as what we put in it is almost in many things that exist, and probably if you go back to the Archer usage, probably 99% of all those interaction was for retrieving the interaction. So if you want to look at the atmospheric condition, that gives you the same platform, a framework when you want to look at the climate phenomena. If you're looking at the interaction between particles, and that's what I was saying, the Feynman famous solution that trying to understand physical state and phase transition for new material discovery. If you want to look at in the financial agent, in order to understand market behavior and economic outcome, is again about the same, retrieval of the interaction. And it goes on and on and on. And just because of the colleague we happen had at the School of Informatics with bioinformatics, so we start looking at the interaction in genomics and trying to understand how quantum might give you a different way of understanding this interaction. And understanding exactly by playing with this weighted connection, can we come up with a new pattern and learning phenomena that would have not come up in the classical? So, okay, now, instead of showing the result is, yes, we've done it and that's this result, I just want to tell you how bits and pieces needed to come together. Because there is a very general framework, which is called variational quantum circuit, that is very popular, is a sort of thing that is shallow, simple, you can more or less implement on the current noisy devices, that you can put them together, and is not too much from any parametric, natural neural network training. And interesting enough, the first thing that we have to do, while a lot of industry saying, yeah, this is it, VQE is the solving of all the quantum problem, all the classical problem in one, we had to go a step back, do the complete mathematical study that I'm referring it in here, to understand, is there really an advantage in quantum? Are we really able to beat classical AI? Because that's a huge problem. We're talking about the devices to be built, with talking about the exascale, NVIDIA coming with the particular problem. So we had to come up with a guideline for ourselves to ensure in what scenario quantum might give an advantage. And that's the destructive approach for ourselves, in the sense that we have actually break a lot of quantum advantage claim that exists, that people say that, yes, we can do this training and this quantum algorithm and get advantage, and showing that by cleverly using classical AI, we can approximate the solution that comes from quantum. Usually my quantum machine learning people don't like us when we talk about this thing, but it's very, very important things to do to be destructive to yourself, because it allows us to completely give us the design that how should I put my quantum machine together so that I don't fall on the path that anyway a classical AI can good enough approximate it. In fact, two things come out of this study. First of all, by showing that there are a method like a random Fourier feature sampling, which is a very nice advanced method in classical, we come up with the quantum inspired algorithm in the sense that it's the algorithm that nobody would have thought about it to design it classically. So we have an artificial algorithm that is as if it's quantum, but we use classical AI to particularly simulate it. And hence we're coming a solution that you can apply it now. But at the same time, also we highlight what should be the design principle. So in this follow-up work that we did, we knew exactly when we want to load the classical data in the quantum machine to take advantage of it, how to put all those building blocks so we don't fall under our own curse of being classically simulatability. So that's what I was saying. So we come up with this very new method of Hamming weight preserving native gate, which beautifully, miraculously is also matching to some of the hardware platform being designed. So this is also an interesting point. Because we're still so close between hardware and software, we actually can talk, this is actually exciting, as if we are at the beginning of, I don't know, 60s, 50s of computer science. We talk to our hardware people, and there is this particular sort of RBS 2-qubit gate that is able to escape our classical simulatability. And this is the Hamiltonian that these hardware people can build it. So this co-design allows us to go one step forward to design in such a way that we don't classically simulate. And that's we come up with this solution. The quantum circuit board machine is a new framework that has been designed with awareness of what is the hardware is going forward, what are the things that classically can be simulated, and hence creating a machine that can target the data. In this particular case, it was for the genomic data that we have access to, that at least I would not claim it is not faster than classical, but there is no naive and straightforward of classically simulated it. And what did we learn when we run it on the hardware? These are very simple toy model, with the 4-qubit, with the noisy model, etc. We just started saying that it works. Okay, so the data distribution that our colleague wanted to have access to, we are able to get them our hands there. So we kind of know that we are walking in the right direction. And interestingly, is also trying to see that in what aspect of reaching the distribution we want and the training loss function we're doing it is we are getting there. So it's really putting the real hardware, the real noise, real training go together. And I think the message that come out of it is still is an ongoing word is that by coming up with the right quantum architecture, and that's the part that's like as if we are doing a little bit like a FPGA programming, if you wish, by telling to our quantum hardware what type of architecture they should be able to build, we are able to reach to these interferences that it might be the case that is because of the non-local correlation entanglement that I was telling you, we are walking in a different space. Does it mean that it's better than classical? I don't know. I don't think so. But it just may be the case, and that's come back to the discussion, we are picking up a different type of correlation. So we have looked at the generative adversarial model to compare our Born machine with the Bayesian model. It's more accurate, is all matching, but what does it mean? Of course, it's subject to the which measure part. So let's put it this way, is just another toolbox in doing AI that it's deserve to be sitting in this full stack. And we're trying to see for time being this quantum inspired solution, but maybe we reach the platform that actually genuinely cannot be classically simulated. So then let me jump onto the other topic that I was advertising, which is also privacy and integrity. So now I want to kind of say that, okay, park that thing that, okay, quantum somehow, because it's talking about quantum correlation, gives you a different notion of speed, if you wish. Now I want to bring the quantum, those magical qubits that I can encode information. When I can communicate them, then I can send them from point to point. It gives me also a completely different notion of privacy. Classically, we know how we're doing privacy and encoding and encryption. We use RSA, we use factoring, we put the problem in a hard problem, and et cetera, et cetera. But here we are entering an area that today, right now, as I will discuss, we can have a future future-proof security. One of the things that might be very interesting for the healthcare, I mean, Mark again mentioned it, that there is lots of paranoia about the health data, but we have for the first time a toolbox that allows us to create security against future attack. What do I mean by this? Because it's very, very important, this concept of future-proof. Did I put something on it? No, so let me say it. So the idea is that whatever crypto system and encryption and etc. that we use today in order to do our health data manipulation or financial sector manipulation, you know that in cryptography you can never have provable security unless it's information security, which is very limited in terms of the size. So that means if tomorrow somebody comes with the clever algorithm, is breaking down. And that's happened. Shor's algorithm came and break down the entire system, and everybody's scratching their head. What do we do against harvesting attack? But quantum communication, maybe I'll have some slide later there, sorry. Quantum communication in this particular way is just giving you a very unique property that if during establishment of the key, you didn't break it down, it's too late. Tough luck, it's gone. Tomorrow you cannot come and say, okay, now I'm going to break it, because we are having, so when it's not about more secure than classical. I don't like that terms. It's actually a hybrid classical and quantum solution, which has a unique property that it has forward security. And in fact, whenever we talk about who cares about this higher level of security, health data has been pitched to us. The only people who probably ever need to really care about such a forward security is military and healthcare, because those are the data that you need to make sure they are secure in 50 years, in 100 years. So now I want to mention a little bit about, okay, now we want to look at the secure communication. That's something that we have being established around the world. I have a bunch of deck of the slide during the discussion. We can look at it to tell where is the status of it. But we also have the way that we can do secure computation, be it the classical computation that you want to do on top of this secure encrypted data, or being quantum computation on this quantumly encrypted data. So that's another roadmap that goes very nicely next to our, if you want, the generative AI, that we have privacy by design rather than postdoc. So some of the people have known that, differential privacy is a methodology that we exactly use in order to provide, for example, privacy of the synthetic data, etc. So what do we do again? Hence, we're picking up the classical framework for differential privacy and we're quantizing it. And why quantization means, what's the right model? How do we define the measure that allow us to say that, yes, this quantumly produced data are noisy enough not to release the identity of the original user, and yet useful enough. Again, I'm showcasing in this work that, we talk to the classical expert and we're trying to get the quantum version. Then we went to the same, what is the way, classical encryption for secure multi-party computing or even federated learning is the thing. And what you're going to do is picking up exactly the classical encryption, and on top of that, you do computation. And we uplifted this thing using the classical encryption that you see in the system in the top, and that orchestrating our quantum computation that we're doing on our quantum encrypted data. So then we had to discuss about how all of our devices that we are going to build in quantum are going to be very noisy. And, one of the success of the exascale is actually classical devices are essentially fault tolerant. They have such a good threshold that you don't even ask ever a question that, is my device fault tolerant or not? Whereas in quantum, we need to really build a fault tolerant system, which we are still far away. But we also want to have a system to be able to tell us, okay, I'm walking in this exascale domain that I don't even know how to classically simulate. Can I verify? Maybe you will call it interpretability to some extent or verifiability, but we really need to answer the question of, is this data that I got out of my machine or generating AI machine actually correct or not? Has it been corrupted or not? So we answer that question. And again, in order to answer that question, I'm highlighting, we use the classical linear programming to enable us to bring it. Obviously, classical ICTs keep popping in all the aspects. And the latest work that we put out is that even if the source that is creating your data encryption, even if the devices that is trying to do quantum computation, if everything is malicious and noisy and potentially trying to grab your data, if we have this minimal client device, which is particularly a simple box, even I can build that one, a single photon rotator. So if we build that infrastructure that I was showing you, this network quantum computer. So you have the quantum computer coming from whatever server provider, potentially malicious, lots of communication is happening, potentially can be interrupted. But if we just put the minimal amount of trust on a single device, which is just producing this random rotation, ask me a question later if you want, but if you want in terms of the size, something that we can ensure that is in my control. Now we are providing information security. So it is actually, for me, is mind-blowing. This is something that I've been working myself a lot on, that by reducing the minimal assumption, we are providing something that, again, classically is not possible because of the nature, because any deviation can be detected. So then you would ask, okay, very nice, fancy stuff. Can you build it? Yes, we build it. You know, there is a University of Rome, which actually put all these bits and pieces. They didn't let us inside the room because we would have break it down. But in fact, even commercially, we were able to build the building block of allowing us this privacy preserving multi-client is the same magical photon that goes from one source to the other source, is randomizing, and it gives us something which is unique is the physical key itself. It gives us something that you cannot break it. So it's available even commercially. And then we believe it can be scaled up, you know, so you put many of those key lines together. And at this moment, what I want to share that the source of your qubit could be noisy and not even perfect. The quantum server could be noisy, but all those green part, those clients in between, which have the minimal devices off the shelf, they could be their smart quantum watch that is just applying a single rotation. That's the only assumption of the trust we're putting. But with this, we completely prepare that landscape that I was pitching at. And essentially, again, the pain point of the privacy for me, using this quantum link, we are doing something by design. It's not like, okay, I take my data, now I put a blockchain on top of it, now I put like a fully homomorphic encryption on top of it, and et cetera, et cetera. No, by design, everything will be private and integrate, verifiable. And more importantly, this is the only way that we are future-proof. So mission accomplished. So we take this case study, we try to bring various bunch of people, mathematician, algorithm, hardware, pizza. And it's just the most exciting part of it is that because we're still at the beginning of this revolution, everybody talks together. So soon when people can make money out of it, maybe all those boundaries will break down. But for time being is the greatest fun to have because we're really trying to see where the real quantum advantage can come. And in order to essentially to say that, you know, we are very much open for collaboration. I mean, this center has just been opened, you know, National Quantum Computing is having this program. And only last week we celebrated in Edinburgh the first ever Quantum Festival week. We had 3 events, which was very unique. We brought 500 people from all over the world, which were either industry or researcher or scientists or government sector, etc. We had the AIM Day, famous AIM Day, which matchmaking the quantum industry challenges with the mathematician and student who wants to work on it. Then we had this flagship conference and the anniversary of a software lab itself. And I think this space is a very exciting space. For sure, a lot is happening in the healthcare. I know that, you know, NQCC is running several models, and I'm very happy to be here and to see how the discussion goes. And one last thing that I want to say is a little bit of visionary. I mean, because we were just saying the same thing even last week, that to me, I feel like, you know, the data machine has reached the level that, you know, there is a separation between, I mean, I'm exaggerating, but hear me out, you know. So business view is always to growth and growth and growth. And, you know, somehow this bias that we have in academia, that idea is so important. We are separating. The idea is being created, whereas all the ChatGPT is having its own life, and there is two separated. And I'm so excited to say that I think in quantum data machine, the forces are still together. We're still having this, you know, highly capable hacker student who are trying to discover, and we're still self-defining our identity. We don't even know where we're going, but for sure, we know that we are creating the next step of civilization. So I'm stopping here.
Wow, thank you very much, Ellen. That's the first talk I've had that ended with the next step of civilization. So that's amazing, actually. A very good talk. And we got loads of questions as well. So we'll rattle through those if you don't mind. And the first the first one, I'm ashamed to say I don't even understand the acronym. So Darren Gates is asking, can you define LSQ in relation to fault tolerant QC, please? You did talk a bit about fault tolerance after that question was asked, but I don't know if
That's absolutely brilliant question, and that's why I had this slide prepared for it, because we coordinated, obviously. So the point is that what's happening right now in the field, what we call physicists are master of coming with the acronym. So no shame, Dave. You know, we say the real thing. Physicists come with the with the random. So NISQ stands for Noisy Intermediate Scale Quantum Computing, which essentially a fancy word for bad quantum computer, which is what we have. Is they are very noisy. We don't know if they are really working, and you know, but somehow people have been running machine learning and getting result on it, because maybe noise is good. Maybe we don't want to overfitting. But obviously we know that these are bad quantum computer. And what's happened during the last year is that we have started, I mean, where we want to be is really FTQC, fault tolerant quantum computing, that we have take our physical qubit, we have built error correcting codes on top of them. And so now we have really good quantum computer. But if you read those numbers, while right now we are talking about everybody, I mean, more or less many people, like I think I put it, you know, maybe IBM roadmap in here. So 100,000 qubit, 1,000 qubit is something we're going to see, but they are noisy qubit, you know, they are physical fragile qubit. LSQ, which is standing in a large scale quantum computing. Okay, let's say that LSQ is like 100,000 qubit comes, but it's become the beginning that we have a bit of error correction. So this LSQ, the area that we believe is in the next few years is emerging, is the word that we don't have fully fault tolerant error corrected quantum computer, but we have managed to make them a bit better. They are more cleaner, so they are performing better. Or maybe I stop in here, but that's essentially the roadmap and the numbers and the vision that people are believing in the field. And if I just want to add the application, many of those applications that I'm pitching, they might require practical FTQC or VLSQ, but people are still playing with these noisy devices as well.
Great. Next question is from Darcy Murphy, which is another definition question. What is quantum sensing enabled solution? What is a quantum sensing enabled solution? What's all that
Very
about?
good question. So I think quantum sensing enabled solution is, in short, is that, so photon, the magical things that we love, it allow you to be more sensible if you wish. So there is the Fisher information that is exactly usually classical sensing is defined in the amount of sensible information that you can detect. So the quantum sensing, by going again from macroscopic shine a laser to the microscopic, essentially using single photon source that is shine on your device, it allow you to up to square root of the, according to quantum Fisher method, to give you a better detection. So the idea of like a sensor, you know, like the example that people are saying, so quantum enhanced, it means that you are building this device and these devices don't need quantum computer. So you really have a much more lower technology that is being built. One of the hub in UK has been leading this thing in Birmingham. And they are building these devices that, for example, you can sense all the hole being digged under UK roadmap. So you don't need to anymore dig to figure out where is the pipe. So you have a higher sensitivity. And this mission that I was putting up, quantum enhanced sensing, it's a little bit of designing, you know, while this initial mission. So we know exactly how to build quantum sensor. We know exactly in where they are enhancing, they are, what is the achievement is there, but there has been the bulky stuff. So I believe this mission is about how to build those devices that still have this quantum advantage that we know it exists in different settings, but being integratable for the medical use, which is a very, very different one. And I think soon we will hear in the, because this 5 mission will also follow up by 5 different centers to be delivering them. And one of those centers is actually biology, sensing, healthcare related. That was my jumble mumble about sensing.
Good. Next question is from Sudipta Chowdhury, who asks, are there any special groups or platforms focused on quantum strategies for healthcare people can get involved in for learning, developing skill? How do you basically on-ramps? Are there any on-ramps for this kind of thing at
I
the
would
moment?
say, like, as I said, the mission, I mean, Mark was telling you, the strategy was written for compute and is still in the coming. So I think the strategy has been announced and this mission are concrete, but we are not yet at the complete delivery plan. So it's not like, this is like, let's get on board. Is for time being, for example, for the Mission 1 National Quantum Computing Center is a natural coordinator. For Mission 2, which is communication, I mean, I would say right now it's not clear who's leading what, and we are exactly at that stage that the government, with the working group that is happening, are trying to define. But at the same time, it's a good moment, means that nothing is set in the stone, and I think I would take the opportunity to invite this colleague in the call to get involved, because I think for me, is always the worries is that if you don't talk with the right sector, with the right end user, we are not actually knowing what we are trying to build for. So everything is on board, and UK, perhaps I should say that UK has the quantum office. So I think UK quantum office is the one which is coordinated the National Quantum Strategy Mission. They will hate me to announce this, but these are the people that you need to lobby and get in touch and, to try to get involved. But the UK Quantum Office is the right person.
Right. And so then Will Whiteley is asking, are there particular, you may not know the answer to this, Ellen, actually, but are there particular health problems, classes of health problems that we should be thinking about? Or is it better to start from thinking about the problems we already understand, like larger data sets with high dimensionality, biobank proteins and so on? What's the best way to get into this, do you think? So I know this is a very difficult question, Dan.
It is a very difficult question, but it's actually the most interesting question in a sense, because the whole point of our Spark program or Quantum Software Lab is exactly, we have been the scientists or researcher or quantum expert. We have been building tools, so we are building tools. We have so many different things, but it's the time and is the most critical part of our technologies to make that match make. I cannot claim a person who's a quantum expert knows that what health problem should we attach, but I would say that there is a lot of mechanism, especially in UK, and I'm bringing this slide on the Spark, which is precisely trying to figure out that, what is the best problem? So because you could say that, well, optimization, NHS wants to have a better allocation of bed, but that's an optimization that would be in energy sector, it would be in logistics sector. So it's a very generic family, and we know this generic family. So if you want to just to know that what are the general set of things, optimization, machine learning, interface. But I feel if we really work together, as I was telling you, because we have a different way of thinking about information, we might even start asking a question that, I said that we want to ask industry pain point, but the reality is that actually we want to introduce new pain point, the pain point that you didn't even know exists. So maybe there are something in healthcare that nobody had thought about it, but we have access to it. So again, I don't know the answer, but I would definitely encourage everybody to get in touch with the Spark program in NQCC, because precisely is the place that they want, without completely, exploring a bank, trying to invest heavily on quantum, just to have this feasibility study. Does it make sense to look at the quantum for this particular problem?
Yeah, good. And then I've got a couple of, I think, more like comments. One again from Will talking about the interaction example and saying that the problem is we don't have enough data in a population to have adequately powered analysis. He means statistical power in the inferences you would draw from the data. If we understand interaction the same way, which is kind of cryptic caveat. I don't know if that's something you want to say something about, Ellen, or whether that is just a generic comment. I mean, we are limited in scale of data sets in the UK because we've got a small population.
I'm making some sort of relevant, it's not the answer, but just highly agreeing that, it's all about scale of the data. And it might even be the case because of the limitation that we have with our current quantum capacity, or even the roadmap of quantum, is those massive, huge data are not the good sandbox for quantum. But yet I want to say that it's sometimes not just about the size of data, although all my talk was all about we are the bigger, we are the better, but it's also about different way of the correlation. So here comes a tricky one. So could it be a data which has a different type of pattern? As I said, again, we played with the in the financial sector for currency exchange. It was not about the size of the data. It was about the different correlation that we were digging out. So I think, again, we know that, for example, our material science discovery, the fact that these data are quantum data will allow us, in fact, knowing that we're detecting it there. So yes, it's not about just the size of the data, it's just about the structure of the data, and we're just scratching the surface. We're just trying to understand when this thing needs to be done classically, when this thing needs to be done quantumly, when it can be the hybrid. So to be continued, I would say.
Yeah, maybe can I just press on that a little bit? Will came back to correct me that we have very large data sets in the UK, but what I've heard, you hear some people talking about future quantum, where they talk about really quite astonishingly large things, being able to include very, very large amounts of genomic information because you've solved a lot of the fault problems. And you can just include vast amounts of information, the world's genomic data, or that kind of absurd scale of thing, and then solve constraints very, very fast with these kinds of systems. I mean, is it worth even thinking about those kinds of systems yet at all?
I mean, obviously the answer is yes, in terms of, because we still need to solve it on pen and paper and thinking that what's the right way of encoding those data, because it's one thing when I'm saying, oh, okay, so we just need to have our qubit and put them together and we break the barrier. It's, as I said, it's not just the fact that I upload those massive data on my superpower quantum computer. Now I'm going to run things differently. So thinking about how the data need to be encoded, what do we want to do with this data, what are the different way of doing it, is now that's the way to do, but with the caveat that what we're doing is a bit of research. This is going to be very different. So if you want an answer for your drug discovery, which is happening in the next 5 years, obviously go with the classical AI, large language model, etc., saying it. But if you want to start thinking about energy costs, scalability, where do we want to go, etc., I don't see any solution but quantum. So by all means, we need to start thinking about it, because that's the limitation. The limitation of classical will be the time that we need to understand how to pick it up.
Correct. And so I'm just checking the question. We've got. I was going to say we're running out of time, but there is one more question. Satis Kumar Jyoti has their hand up. If you would like to shout.
Hi. Yeah. It's a very nice presentation and great work. I have been related to quantum noise and uncertainty, how you're handling and designing a quantum sensor in terms of quantum noises and uncertainty.
It was very noisy, your question, because I heard half of it. So I think you asked
I will
about
come again. Yeah. Maybe I will come again. Quantum noises and uncertainty, how you're handling these two in terms of designing a quantum sensors.
A quantum sensor. So let me answer it a little bit general, because it's actually very important. So uncertainty principle, as it is actually what we love, because it's actually is a feature. So it's not a bug. The fact that you have this uncertainty principle, that you cannot have momentum and speed at the same time, that's the feature that is very essential for measurement, disturbing the system. So that's why we're using it. But the noise is our curse. If we could have control of this system, there was no correlation between this quantum device and classical, we would have quantum computer and perfect system and perfect devices. So that's the bottleneck that we're trying to answer. In case of sensing that you mentioned, in fact, because our system that is usually used for sensing is our single qubit system, or a low number of qubit system, the noise is not as crushing as it is for quantum communication and quantum computation. So if indeed, if your system is too noisy, any quantum enhancement that I was mentioning will be disappear and you'll come back to the classical sensing. But the whole proof of concept demonstration and devices that has been built, because they are isolated qubits, you can avoid those noise. So this for me is the way to answer it. So uncertainty is there and is the reason we get advantage, but quantum noise, we have to deal with it all the time.
Fantastic. So many thanks, Ellen, for taking the time to do this. It's
My pleasure.
really
Thank you very much.
eye-opening stuff, and also to the other talks we've had previously. And we have another 3 discussions to have a little bit closer to home from people who have been spending some time also with HDR UK. So hopefully that will be a nice contrast. And so we're on to the last tranche of our discussions. This one led by Honghan Wu, talking about, kind of links in very nicely to the stuff that we had before in the first sessions, talking about generative AI and all of that. So Honghan, can you lead us on?
Right. Yeah, hi everyone. Good afternoon. I hope we had a good break. So yeah, as Dave said, this morning is more about all the tools, fantastic, impressive tools, like hybrid AI, Excel computing and quantum computing, and how. And my talk is more about how we're going to use these tools, supported technologies in AI. Specifically, I'm talking about some of the work we are doing recently about evaluating generative AI models in biomedical tasks. So basically just evaluation, no kind of new models at all. Okay. And again, Dave, I'm not going to talk about bias today. So possibly in the future, I'm going to talk about bias of these models. It's kind of an ongoing project we're doing as well. Okay. So before that, you might ask, okay, what kind of generative AI or language models we can use for medicine? So it's quite recent, and Hugging Face published, colleagues, including those from Edinburgh University, published benchmark or leaderboard of medical domain-specific language models, large language models in on Hugging Face. It's quite nice web page. It's kind of, I think it's quite, it's late last week. So it's about a dozen also language models, so particularly adapted for medicine. So I really recommend people take a look. So just give some kind of screenshots here. So essentially, they evaluate all these models using these typical benchmark data sets for language models, like there's MLU, medical MCQA, and MedQA. So that essentially is a question answering questions. So you can see this on the top and the right bottom. You can see this ranked list. MedPalm 2 seems the best, the average score on all these benchmarks. GPT-4 is about number 3. So that's more or less the current leaderboard. So all I'm going to talk about is different way to evaluating these language models, and not from a purely QA point of view, more from a task, different aspects of the evaluation from biomedical task point of view. I'm going to talk about 2 things. First thing is about the question, is it still valid or sensible to do traditional NLP, natural language processing? So when I say traditional, which means that you have kind of embedding models, convert your text into a vector, then apply whatever traditional classifiers like random forest or LSTM, small kind of neural networks to do NLP, or some kind of small language models like BERT-based approach, do some fine tuning to do that kind of stuff, compared to the current, large generative AI, GPT-4 or other, as you see in the previous slide, so many different language models, large language models out there. Is that still valid? We do that kind of stuff, or we just, shift our paradigm to purely using generative AI for biomedicine tasks? For this first part, I'm going to talk about knowledge graph enrichment as a particular task. The second part, I'm going to talk about multimodal large language models in their hallucination test in medical visual question answering tasks. So it's particularly focused on one aspect we all know associated with general AI, which is hallucination. Okay. So the first task, bit, we have a preprint out there. Feel free to take a look if you're interested in the details of the work we did over there. So just to give you background, what we did is we focus on one ontology, or we call it database or knowledge graph, whatever. So it's called KEBI. So KEBI, the full name called Chemical Entities of Biological Interest. So it's one example of knowledge graphs that is used a lot in the interdisciplinary field between chemistry, biomedicine. For example, things like drug target identification, drug repurposing, for example. So for ontology like KEBI, this knowledge base or knowledge graph needs to be updated regularly because this comes from the literature, from the most recent research in the particular field of chemistry or for drugs, for example. And to update those, currently the approach is mainly manual process, of course, with some kind of semi-automated approach, primarily mainly through human update. So which, as you can imagine, is very time-consuming task. So what we did, we'll focus on one particular aspect of this kind of knowledge graph enrichment. Is just very simple. As you can see here, it's a kind of triple, talking about medical component has a role in androgen. So given we call it triple, basically a small sentence. You know, we have subject, predicate, object, and three components of the triple. The task is very simple. Just say yes or no. This is a correct sentence based on the true knowledge. Okay. So what we did, we create three types of tasks for this binary classification. Task number one is quite simple. We just pick half of these triples from KEBI, then randomly generate false triples using the subject, predicate, object from the knowledge graph. Of course, these triples do not exist in the current KEBI ontology. Second, true versus random false triples. The second one is task 2 is called true. Again, the same. The wrong one or false triples are those wrong direction triples, which means that we just swapped the subject and object. In this case, as you can see on the right-hand side, just change the subject to androgen, which actually should be a raw. Apparently, this is wrong, right? And task number 3 is true versus wrong object triples. We try to make task 3 a bit harder, which means that we change the object or subject to enabling entities, which means that change to their sisters or brothers, which they share the same parent, which the triple doesn't exist in the knowledge graph. So you might imagine that's more difficult because they are similar, they're siblings, they have 5, and they have similar attributes, but actually the given triple assay is not true. So basically that's 3 types of tasks. Try to do the evaluation. So essentially that's the whole study setup. The left-hand side, as you can see, we just show all this model we used. So the x-axis basically shows the corpus size for training these models. The biggest ones you can imagine are the GPT models, including GPT-4. The smallest ones, the random representation, actually we just generate random vectors for each words in KEBI, trying to see how this very simple model or embedded model actually, how they form this kind of task. And the y-axis shows the domain relevance. So some models are more relevant to the domain we're working in. For example, word2vec chem, which is the word2vec model we further trained on the chemistry domain. So I'm not going to go into detail, basically different models we tried. I just mentioned this PubMed-BERT is kind of smaller language model, BERT-based model. And that's the another language model use. All other things are embedding models, basically convert a word in KEBI to a vector. That's what we mean by embedding model. The right-hand side are the tasks. So we show the 3 different tasks already. then we have 3 different NLP application paradigms. Try to see, the first one is in context learning using GPT models, generative AI. We use the GPT-4 APIs. We also use GPT 3.5 as well. And the second paradigm is kind of fine-tuning PubMed. Just take the PubMed as it is, do a bit fine-tuning for the binary classification tasks, then that's the model we're going to use. Then the right-hand side is called traditional NLP. We're using these embedding models, convert the text into embedding. Then using embedding, feed these embeddings into binary classifiers like random forest. We're going to talk about details over there later. So 3 different ways to do NLP for these tasks. Then we compare these using the training data set we generated from Cabby. We also try to change the training data sets in a different imbalance ratio. For example, at the beginning, we're just using 9 versus 1, which means 9 training data set versus 1 test data set. We have loads of data. To the right-hand side and more, the other end of the spectrum is a very small number of training data set, 1 versus 9, which means that only want 10% of data for training, but have 90% of data for testing. See how these models perform in these different setups. Trying to get the idea to say in what situations, which model, which paradigms works better for this knowledge graph enrichment. So this is a data set we have. It's quite, so 3 tasks, each one is about 600,000, in total 1.8 million triples we used. This is a 9:1 kind of ratio for training and testing for the default setting. As I said, we actually gradually change these ratios to test different model performances. So first, we're trying to answer this question, the sub-question. So how do these foundation models like GPT-4 perform in these kind of curation tasks, like 3 tasks we mentioned, including different ways, different models, and the different ways of prompting these models. So just show you, I hope you can see it, left-hand side, just basic prompting, essentially give 6 examples to do 6 short learning. So basically 3 of them are true, 3 of them are false, to give as examples to GPT model. Then ask the model to predict a new given kind of triple. Okay, that's the basic prompt. We actually have 3 different prompt formulations. The first one is base. The second one, we just ask the model to say, if you are not sure, for example, if you don't know the answer, please just say, I don't know. Don't give the yes or no answer. This is aimed to reduce hallucination for these models. Prompt number 3 is a variant. We just change those. The base prompt, 3 positive, 3 negative. And then in the number 3, basically we randomly put this true and false triples as examples. You might think, what does that make a difference in the result? Actually, it makes a huge difference. So you will see this difficulties to have a proper prompting for your task is kind of challenging. One of the challenges we're going to see in the result. Okay. So this is the huge table. I'm not going to talk about every single numbers here. Just look at the bold text, which is the best performing model, and setup, which essentially performs the same. GPT-4 using the prompt strategy number 3, which means that using random orders of the examples given to GPT-4 actually makes the model performance better for whatever reason it is. And conclusion on the right-hand side. So first, GPT-4 compared to GPT 3.5, BioGPT is the best, not surprising. BioGPT performed poorly. Conclusion number 2, prompt number 3 gives the best performance based on F1 score. Okay. And next conclusion is sometimes there are significant numbers of cases the models not confident enough to give you answers. So if you look at the first column, which is accuracy, we just exclude those, we count those examples, those samples, the model cannot give a confident answer as a negative result. We still can see this about 83 kind of accuracy, the best one, to 84. The right-hand side precision reconnect one, which is exclude those answers, those examples, which the model are not confident. You got the numbers that are looking much better, but basically we just remove those, and the model could not give an answer. So, which means that sometimes you have to accept that this model as it is cannot give you all the answers you want to the model give you. Conclusion number 4, task 2 seems most challenging for GPT 3.5 and also for GPT-4 as well. But for GPT 3.5 seems extremely difficult compared to other 2 tasks. GPT 3.5, the thing I want to mention, the last one here is we do this experiment in 2 different time points. One time point, July 2023, and the other one, December 2023. The difference of performance between the different versions of GPT 3.5 is significant. GPT 3.5 got improved all the time. That's another problem with this commercial API. Sometimes you cannot reproduce the performance all the time. Okay, so second question. So what we try to answer is, can smaller domestic embedded models compete with large language models? The answer is yes. So this is a kind of head-on-head comparison between GPT-4 and basic models. The conclusion here is pre-trained machine learning and BERT models are better than GPT-4. That's the result tells us. And the domain adapted small models like embedded glove-based embedded models actually can perform really well. And PubMedBird performed particularly good on task 2, which is the most challenging task for GPT-4. That's just an observation. We don't know the reason of that. The final question is, are supervised learning approaches truly obsolete in such tasks? So these figures basically, they're different colors, okay? The dashed lines, the GPT-4 performance is 3 different tasks. And the x-axis, we just change the ratio of training and testing from 9:1 to 0.5 to 1. As you can see, when you have fewer training data set, the GPT-4 actually exceeds the machine learning or fine-tuning models for task number 1. But for task number 2, actually for the extreme case, the other models are still better than GPT-4. For task number 3, actually is different. That's supposed to be the most challenging task for machine learning. Even from 7 to 1 onwards, GPT-4 shows the very usefulness without any training, just using 6-shot learning. That's performed very, very good. So which means that if we don't have very good data for training or large data for training, then GPT-4 can be a very good assistant for your task. Okay. So I'm looking at time. Do we still have time for Dave for?
We've got
Yeah, maybe I can skip this one.
Yeah, maybe skip that one because we'll be pushed for time.
Yeah. Okay. Just one evaluation for this. Yes. Okay. Cool. I may stop here.
Oh, okay. I said that so that we could maybe have a question, but maybe it could be you prefer to give a little bit. We've got a couple of minutes. I don't know. Actually, I think it's maybe better if we keep to time because otherwise everything gets compressed.
Yeah.
So does anybody have any questions in the short amount of time remaining? I mean, my question actually, if I can sneak a question in just for a minute before we move on, longhand. I mean, you've got a bit of experience here now. And the results that you've got, if I understood them correctly, are equivocal. It depends on what you might do, whether you go for large language models or whether you go for more specific trained machine learning approaches, would depend quite a lot on the quality of data you had. I mean, do you have any message for people about how to get into this? Somebody who is starting to do this, what would be the right approach?
Yeah, so I think the main takeaway message is we have so many tools in our back, right? you really need to consider which tool to use. And the experiment showed us if you know, the final head-to-head experiment only used 10% of the data, which means that's a very small number, about a few thousand triples. If you have that level of training data set, you can already use machine learning to exceed the performance of GPT-4 as it is, used as it is for these knowledge enrichment tasks. But say if you in situation which you don't really have, or you needed a lot of effort or cost you to collect training data set, and GPT-4 can be a very good tool to start with. So basically that's the takeaway message.
Yeah, that's clear. Good. Any further questions for Hong Han? I'm mindful of time. Sorry, these last talks are a little bit compressed, but that's just the way that this swung through. Oh, one more. Sathis Kumar Jyoti, would you care to shout something?
Yeah, thank you. Very nice work. In terms of like, you said like few thousand triples, but when you look into like, for example, Chem, Bed2Vec Chem and GlowChem, they got like more data, more triples that can be used. So if you use like, for example, 100,000, do you have any kind of limitations, like a threshold there where it what is the amount of data that we may need to use in terms of moving from GPT-4 or to the other models, like pre-train our existing models? And also, did you have compared with the some of the open source models like Llama, for an example, Llama, and then Microsoft, a smaller model like PH3, these kind of models? Yeah, if you throw some light over there, that would be helpful. Yeah.
Yeah, it's a good question. So we haven't tried open source language models for this particular task. We actually do working on smaller models like Microsoft 5.2 already. I know 5.3 is being released soon, or at least the report is coming out already. But that might be a very promising way to use small models like 5.2, 5.3 to adapt it for particular task. For these machine learning and model compared to GPT-4, as I said, if you have a few thousand to about 20,000, sometimes depending on the model you use. For fine-tuning, you might need less data. For machine learning, you might need a bit more data. But if you have a level, a few thousand to 20,000 triples actually can compete with GPT-4 significantly in terms of performance, F1 score, that kind of stuff. Yeah.
Great. I think that's all we have time for this one. So thanks, Hong Han. And now it's time for Will Whiteley, who I believe, in a slight change from the agenda, is going to talk to us about cerebral vascular disease.
Well, thanks a lot for the invitation. It's delighted to speak to you. And I'm sorry I'm not speaking to you about causal inference and randomized trials. I realized actually there was an HDR UK meeting on Friday all about that topic, and I'll share the links with you if you're interested. So I'm going to talk to you about something I've been working on for some time, which is more prosaic than the topics we've been speaking about so far. So certainly nothing as advanced as quantum computing, but it's a disease where using data that's available on electronic health records is really the only way of studying this disease at scale. So what am I talking about? So I'm talking to you about something called cerebral small vessel disease. So cerebral small vessel disease is a finding on a brain scan, and in front of you is an MRI scan of a person on the left with cerebral small vessel disease on your right, the type of brain scan that you would hope to have, a normal brain scan. And the scan on the left shows the damage that we would expect due to a loss of blood supply to the deep matter of the brain. We can see that around the, I'm just going to give you a quick pointer here, that around the ventricles, these are the ventricles of the brain, there's white matter, which we don't see on, there's these white matter hyperintensities, and then in the deep white matter, there are these lacunes or holes, and these, this is a finding that's been known about for some years, but have become increasingly prevalent as more and more people have brain imaging. So why is this important. So let's first of all think about how common it is. Well, this is quite a common finding on brain scans. So if we define cerebral small vessel disease as either the presence of silent infarcts, those are the lacunes I just showed you, or white matter hyperintensities. If you're under 30, hardly anyone has it. By your time you're in your 30s to 50, about 2 to 5% of people have it. Between 50 and 70, somewhere between 5 to 10% of people have it. But in older years, it becomes very common. And the more we look with more detailed scanners, the more we find. Right. So we know that lots of people have what seems to be ischemic damage to the brain. The question is it something that is important? Well, it is, because if we look at the presence versus the absence of these conditions, we can see that people have a higher risk of either dementia or stroke. So if we take populations of people who don't have dementia or stroke at baseline and follow them up, we find that those people who have white matter hyperintensities have about double the risk of dementia in the fullness of time, and roughly the same for people with lacunes. And if we look at the risk of stroke in the future, it's about 2.5 times, both for the white matter hyperintensities and lacunes. So what we're seeing is a marker on the brain that's a risk of future disease, serious diseases like stroke and dementia. And it's something that's measured at scale right now that should be relatively easily available. Predicting the future occurrence of dementia is something that's quite a hot topic at the moment, because there are markers you can measure in blood or cerebrospinal fluid, the fluid around your spinal cord, which also predict the future risk of dementia. And the magnitude of the effects of these blood biomarkers for predicting future dementia is about the same as this commonly measured marker that we find on brain scans that are done routinely. So what we have is we have a common finding that is associated with the risk of serious brain disease that has implications that can be implemented right now in practice to see if we can find people who are at high risk of dementia. These biomarkers are not currently in clinical practice. So what we'd like to do, of course, is to try and find treatments for dementia. And what we'd like to do is to find people who are at highest risk in order to reduce their risk of dementia and try and find them for trials of new treatments. And so what we probably need are large studies of this condition so that the expected effects of new medicines can be detected. So in favour of these large trials is that if we look at the population of people who have this finding on their brain, over the course, every year, about 5% of the kind of people who have that finding, about 5% of them develop dementia, and about 15% of them develop mild cognitive impairment or dementia. And that's the kind of rate of disease that's then possible to study in a trial. There's no doubt that any intervention that we can use to reduce the risk of future dementia in people is going to have a moderate effect. You will have read in the news about the anti-amyloid antibodies, which are of great excitement and maybe will make billions of pounds for the companies that made them, but they have a modest effect on the progression of dementia of the order of 20 to 25%. And that means that if we're going to prevent dementia, we need large studies. If we're thinking about using this finding, this covert cerebrovascular disease, as our risk of dementia, it's so common that if we're going to try and prevent dementia in these people, we need to do something simple that can be adopted widely. So that means that a large trial is the kind of thing that we would be aiming to deliver. And if we look at the rough size of that trial, we'd need about 4,500 people to take part. Of course, we know that dementias have got a long prodrome, so we may not be able to see an effect over the 5 years of a study, and there may be particular things about different people with small vessel disease. But if we think about our challenge, which is how are we going to recruit this number of people who are asymptomatic, that's something we need to use. That's a problem we need to use existing records to try and solve. So how are we going to do it? Well, one place we could start is by using existing data sets of brain imaging that are available to study and potentially available to approach people. So I work in Edinburgh, so NHS Scotland, the nation is about 5.5 million people. And 5.5 million people is large enough to study a common condition. And it's probably small enough that I can ring people up that we're relatively flexible in getting things done. And the resource that's been developed is something called the Scottish Medical Imaging Initiative, which is a resource owned by Public Health Scotland, but has recently been studied in great detail by the University of Dundee in the Pictures project. That has about 1.6 million brain images running in clinical practice from about 2008 to about 2018, and hopefully over the coming years from 2018 to 2024. And each of these images can be linked to dementia and other neurodegenerative illnesses and stroke in the medical records. And so we've got about 1.66 million images, and there are kind of in this population there are about 40 to 50,000 people who've developed dementia. So this is an ideal population to start our study on. So the first question is, how are we going to find this phenotype of cerebral small vessel disease in these electronic health records? Usually when we're studying a condition in electronic health records, we're expecting to find that the condition is somehow coded within the data. So many of us will work in hospital episode statistics or death records where we'd expect to find conditions coded with ICD-10, or in GP records where we expect to find conditions coded with SNOMED. Well, for an asymptomatic condition like cerebral small vessel disease, there's no ICD-10 code and there's no SNOMED code, so we're going to have to use the unstructured data to try and find the presence or absence of these. So working with these people, some of whom I think on the call, Arlene Casey I've seen, and Honghang Wu who's just given the talk before, we developed a rules-based natural language processing algorithm which was relatively simple, but for us enabled us to identify 24 phenotypes on each brain image report, and that worked quite well at scale. So for those of you who aren't familiar with natural language processing, it allows a detection of negation. So here, for example, this particular report says no evidence of significant small vessel disease, so we know that's absent, but it does have a frontal old ischemic stroke, so allowing us to tell that this is a cortical old ischemic stroke present on this scan. So we developed this technique, and this is some time ago. It was clearly natural language processing 1.0, but it worked well. So if we look at all these brain imaging reports, so now we're looking at in about 1 million brain scans, we found about 200,000 people with cerebral small vessel disease, about 216,000 people with brain shrinkage or cerebral atrophy, about 150,000 people with ischemic strokes. But it also allows us to study conditions that have been very difficult to identify at large scale. For example, a tumor of the lining of the linings of the brain called meningioma, which is a common finding, but is rarely been studied in more than a few hundred people, and we've got 9,000 cases. How did the rules-based system work? Well, it worked very well. So for the two phenotypes we're thinking of cerebral small vessel disease, it's got a very good precision. For both small vessel disease and deep old infarcts, these are the kind of strokes that we see in people with cerebral small vessel disease, as well as a very good sensitivity. And that's where we use a clinician's read, so that's a radiologist or a neurologist read of the radiology report and comparing those results to the natural language processing output. If we compare the natural language processing output with a researcher reading the brain scan that the report is associated with, the sensitivity drops because most clinicians don't report cerebral small vessel disease in every scan, but where it is reported, the precision is very good. So although we are using old technology, which is now developed some years ago, we've now got a tool where we can identify this condition, which is otherwise asymptomatic and uncoded at scale. So what do we find? So what we've done first of all is try to look at whether we can replicate the risks of dementia and stroke after a finding of covert cerebral small vessel disease in the previous bespoke research studies in NHS Scotland data. So that data that is collected from routinely through the provision of healthcare. So of about the 5 million people who are registered with NHS Scotland, about 400,000 had a CT or MRI brain scan, had complete data linkage and a brain image report, and had no stroke, Parkinson's disease, dementia, cancer, or epilepsy prior to their scan. So this is giving us these are the number of cases. So we've got 130 cases of people with cerebral small vessel disease with no prior disease, compared to about another 250,000 people with no prior disease with no cerebral small vessel disease. Unsurprisingly, these people with this damage are older compared to people without this damage, but they're about as deprived as one another, and they're about as likely, and their sex balance is about the same. So what did we see? So if we looked and found if we looked and defined the presence of cerebral small vessel disease by the presence on a brain image and followed people up in the very long term for the incidence of dementia, stroke, or Parkinson's disease, we find that cerebral small vessel disease is associated with a rough doubling of the incidence of dementia, about 2.5 times the incidence of stroke, and about 1.5 times the incidence of Parkinson's disease. Also, because this is an electronic health record research, we want to see if there are conditions to make sure there are no associations with the conditions we don't expect to see an association. So if we look, we don't expect to see an association with another brain disease, epilepsy, and indeed we don't, nor do we see an association with another disease of aging, colorectal cancer, so we see no association there, so giving us more confidence that this association is causal. And in addition, if we compare our estimates with those of bespoke population-based studies where people are recruited specifically for the purpose of studying small vessel disease, we found our associations are of a very, very similar magnitude, although of course our confidence intervals are tighter. And they compare to a similar natural language processing study that was done in California by a colleague who found similar estimates. So I think what we can summarize is that the dementia and stroke incidence with small vessel disease measured in clinical scans in Scotland is similar to clinical scans in the US and bespoke cohort studies, meaning that we can think about how to approach people with covert cerebral small vessel disease using their electronic health record. And this is something that's been done for larger trials of treatment in cardiovascular diseases and diabetes, where, for example, the heart protection study or Ascend approached 400,000 people with diabetes to take part in a study of 10,000 people of the medicine aspirin. So we are at the moment working to see if we can implement a data pipeline to see if this is acceptable to people with covert cerebral small vessel disease and find out roughly how many people respond to our invitation. So I'm doing this work with Joanna Wardlaw, Professor of Neuroradiology, and Fergus Dobell, funded by the Chief Scientist Office. And so within the data lock resource in NHS Lothian, that's the area around Edinburgh, we are seeing whether we can implement our NLP system within a clinical-based system to identify and approach population, and then to see whether we can approach those people by letter, and are co-developing with people who've been affected by conditions how to do that, and that's working together with NHS England's Digitrial service. So first of all, before I conclude, apologies, if you do want to know about clinical trials and causal inference using AI, I'd suggest you look at this lecture by Miguel Hernan, who is really the person to go to on the topic. And there was a fantastic conference by an HDR UK adjacent collaboration between Miguel Hernan's group and the University of Bristol group led by Jonathan Stern, and that will soon be online. So where are we going next? So, covert cerebral small vessel disease is an important marker of really some of the diseases we're all worried about for the future. So we need to take a public health approach, and so that means working out how to do these, study this disease at scale, and really only by using the data held by the NHS and implementing advanced methods can we do that. So I've told you about natural language processing. The next thing we need to do is to try and use the images themselves at scale. So we have a funded project by University of Edinburgh and Dundee to do that. We need to work with patients on acceptable trial design. So we're trying to see whether our automated approach works. And then we'll be identifying suitable treatments to use at a large scale. So if you're interested in this work or interested in using imaging at scale, please let me know, because this is a topic I've been working on for some time. So thanks very much for listening. Sorry it wasn't quite what you wanted, but I hope that was of interest to everybody. Thank you.
That's great, Will, and there was no expectation about what we wanted, so no need to apologize. It's we're very open to ideas. We have a question in the chat from Jose, who's asking, I'll just repeat this, how widespread is the practice of these brain scans, and could there be observability issues leading to confounding, i.e. people who get brain MRIs are more likely to be sicker, which could possibly relate it with higher risk of dementia? Have you tested whether the presence of any brain MRI has any predictive value?
Yeah, so Jose, you're right. Of course, the population who get the brain scans tend to be older and sicker than those that don't. So if we're thinking about causal inference for, if you like, the presence of this condition biologically, then we might be better looking at something like UK Biobank. However, the problem that we need to solve is the fact that there's not going to be any time soon, at least in Europe, where people are going to get brain imaging screening for their health. And secondly, there are plenty of people who told they've got this finding through the process of their normal healthcare. So we need to study this problem in healthcare, not just in kind of bespoke populations. So although you're correct, the reason we're studying it in this population is that's the clinically relevant one.
Any more questions? A quick curiosity question from me. Oh no, here's Satis Kumar Jyoti is asking a question. Here we go.
Thank you. Is it like, I'm wondering, you combine both, is it a multimodal, or it's kind of like a image, you understand image, you predict using image, and then you use NLP as a report data as a different model, and then you combine at the later stage, or you use both image and unstructured data, like the report data together, in terms of for predictions?
Yeah, so far we've only used the report. We decided to start there because we had a technology that we thought would work and it was going to be tractable. We're starting now to see whether we can use both report and images. And the challenges we're going to face there are, how do we look at such a large amount of data? How do we deal with the variability across different scanners across the country? And what kind of models do we need to use to identify these conditions? So these are currently research problems. So what we probably will end up doing is using the reports as a basis of exclusion to determine our image-based set when we start working on the images themselves.
Great. And a question just came in on the chat from Dave Cameron. Question is, how could you use this approach to identify novel or non-validated risk factors, since we don't understand all factors that increase or decrease the risk of disease?
Yeah, so I think it's possible to, clearly it's possible to use electronic health records to examine risk factors, but I think I think it's always important to have at least backed that research up with research with causal questions, so perhaps a causal design, target trials and the rest, as well as using less confounded methods like Mendelian randomization or studying in different cohorts. So I think for identifying risk factors, it's probably one part of a kind of causal triangulation. For studying unrecognized risk factors in healthcare, it's a way of approaching people and seeing absolute risks for different people.
Right. So I see no more questions, and we're just working fine for time. So the last one in our sequence is now Mobola Faloa to talk about causal machine learning.
All right. Good afternoon, everybody. Yeah. So you can call me Mo if that's easier to pronounce. Yeah. I've tried to just use myself by saying the best presentation was less. For the last, this presentation is the best, so that's why I'm taking it last. Anyways, so I'm glad that Will mentioned a bit about causal inference, so which kind of gives me some ease into my presentation. I'm going to be speaking about causal machine learning, causal ML as an alternative to classical machine learning. So I'm not really going to be speaking so much about the technical bits, but I'm going to be speaking about its applications in health for research and for public health policy and all of that. So just a moment. Okay, so just to give a little bit of background before I go into causal machine learning. So health data we know is large. It's we have large number of attributes. We have it's multimodal. We have different representations. We have text, images, even sometimes audio, and we have a lot of complex relationships within health data. And of course, all of these kind of requires or necessitates the need for us to use advanced computational techniques to draw out meaningful insights. And then one of these popular techniques is machine learning, as some of the speakers have already mentioned. And this technique has been very useful in health for modeling disease progression, for disease diagnosis, predicting outcomes, disease outcomes, or even treatment outcomes. And then also very relevant for risk stratification. So we're able to, with machine learning techniques, we're able to identify risk factors for certain diseases. So why is all of this important? Now we know that the goal for healthcare systems is not just to predict disease, but we want to prevent it. That is what public health is all about. And we are moving towards precision medicine, which has the aim to just capture individual treatment responses and tailor interventions to personalized care. So basically, we want to do this by building clinical decision support systems that provide insights that are actionable, that provide individualized treatment, so that we can provide interventional treatment decisions. And then we can only achieve this by looking at cause and effect relationships, rather than just looking at patterns or correlations in the data. Now, I'll just speak briefly about classical machine learning and its limitations, and why causal ML is sort of a better alternative to use in the healthcare setting. So as I mentioned before, classical machine learning has been really helpful for risk assessment, disease diagnosis, and treatment planning. We have used different algorithms like logistic regression, decision trees, and random forest, popularly used. However, this methods or this approach has the limitation of correlation, which is that it just identifies patterns in the data, and it's often limited in identifying causal relationships and treatment effects. Now, one other challenge that classical machine learning has is the adoption. So because there are often issues or challenges around interpretability and transparency on how these models make these decisions, and then there's sort of some limited understanding of how they are making their decisions. However, even though we have some methods to interpret how these models work, it's usually not sufficient. You know, it gives this sort of black box approach to things. So now we'll go to causal machine learning. So causal machine learning is just an advanced field intersecting traditional machine learning, of course, and causal inference. Causal inference is a technique that is commonly used in econometrics. So causal machine learning just brings together the traditional machine learning that that does the prediction, and then causal inference. So we've often heard this, that correlation is not causation, and it's just important for us to be able to, as I mentioned before, classical machine learning just points out patterns, shows us, oh, these variables are associated with the outcome, but not able to actually tell us which one causes the other. So what causal machine learning does for us is that it goes beyond identifying patterns, but to understanding how we can change one variable to affect an outcome. So as I mentioned before, that the goal of precision medicine is actually to take actionable steps or have interventional treatments. And we can only do this by observing cause and effect relationships, which causal machine learning or causal inference methods gives us the opportunity to do. So why is this important? This is important because unlike traditional machine learning, causal ML answers questions like, how will a disease progress if a patient is given treatment X, or would a patient still have experienced a particular outcome if they were given a different treatment? And to answer these questions, we need to understand cause and effect relationships. We can't just we can't answer those questions by just looking at patterns. And this is very important because it helps us to make more informed and effective healthcare strategies. So some of the concepts that are important for us to just note in causal machine learning are first, propensity score matching. So what does this do for us, or what does this mean? This is a causal inference technique that balances the distribution between confounding variables between the treatment and the control group. So we know that confounders are a huge concern for classical machine learning. So, but with this causal inference method, we can actually balance the distribution of confounding variables. Another thing that is important for us to note is counterfactual analysis. So what does this actually mean? So what counterfactual analysis does is that it allows us to estimate individual treatment effects, and also look at that. So what that does, allows us to estimate individual treatment effects. So what that means is that we're able to look at the difference between what will be the outcome if someone has a treatment or if they don't have that treatment. So, okay, so I'll explain that better in this slide. So some of the principles of causal inference, as I mentioned earlier, the counterfactual framework. So what this does is enables us to estimate what would have happened under different treatment or intervention scenarios. So we can look at what would happen if someone has a treatment or doesn't have a treatment, which is usually impossible for us to look at, because what we can do is most times we can look at an effect of one intervention per time. But with this counterfactual framework, we can actually just look at both potential outcomes. Another thing is heterogeneous treatment effect. So one thing that causal machine learning or causal inference helps us to do is also to, beyond estimating treatment effects, we can also look at the variation of the treatment effects across different subgroups or individuals. And then this actually is the part that is very important for personalized treatment strategies. The third one is causal graphs. So basically, causal graphs are just visual representations used to depict cause and effect relationships. So what the graphs just do is we're able to see how we're able to identify confounding variables. We're able to identify instrument variables, and then also variables that directly affect our outcome. So I'll take us through how the process of the causal of implementing causal machine learning. So I'll try and do this in comparison to the way traditional machine learning is done. So for causal ML, like similar to traditional machine learning, the first thing we do is to have our data. So we gather detailed data that has not just the traditional features, but also variables that we have, through domain knowledge, assumed to have a causal relationship with the outcome. And then we go ahead to do a causal discovery. So with causal, what we do in causal discovery is just to construct the causal graph. That's the directed cyclic graph. So this is just the graph that identifies or visualizes the different pathways or the different causal pathways in our data. And then the next thing we do is go ahead to measure treatment effect. So the next step will be to estimate individual treatment effects or outcomes under different intervention scenarios. And then we go ahead to build our causal models. Now, how we build our causal models, as I mentioned before, causal machine learning works with the traditional machine learning and then causal inference. So we use a method that is called double machine learning to just learn the relationship between features and outcomes and between treatment and confounders. And then we are able to isolate this effect and then look at the effect of treatment on the outcome. And then the next thing to do is to evaluate the model. So how we evaluate the model is to look at how robust our model is in identifying cause and effect relationships under certain assumptions. So as we said, in causal machine learning, we don't have target variables like we have in traditional machine learning. So what we do to validate or evaluate our model is to add a random common cause for the outcome that we are looking at, and then we look at the impact of the measure of our treatment effect, basically. So we just look at if the treatment effect has changed after just adding a random common cause. And then finally, based on the results that we have, we can now make any decision from the causal insights that have emerged from that process. So what are the advantages of causal machine learning in healthcare? The first thing is explainability. So with causal machine learning, because we are able to construct a causal graph that shows causal pathways, we're able to actually explain how the model has made this decision, basically, and then it gives more explainability to the machine learning model. Another advantage is the personalized medicine. So as I mentioned, that the goal of healthcare systems is to not just predict, but to prevent diseases. And that can be done by just looking at cause and effect relationships. Now, estimating heterogeneous treatment effect, that is the variation of treatment effects across or between different groups or individuals, allows us to be able to actually tailor interventions to specific people rather than just give a general intervention. And then the third thing is to advantage of causal machine learning is and it can help to enhance research. So with causal machine learning, we can have comparative effective research by comparing different treatments and interventions, and then look at their impact on patient outcomes. And then this is important for researchers, for policymakers to foster advancements in research and healthcare innovation. So some of the considerations that we should look at are, first of all, for us to be able to adopt or maximize the benefits of causal machine learning, there's need to be interdisciplinary collaboration between data scientists, computer scientists, healthcare professionals that have the domain knowledge, and then policymakers. Some of the future directions and opportunities that exist are causal representation learning, causal discovery, and causal reasoning. So for causal ML, you can just pick some parts. For example, for causal discovery, you might just want to do a research or a project that just looks at causal pathways within a specific data that you're working with. And then last consideration here is ethical and regulatory guidance. So it's very important that for us to use causal machine learning, there are ethical guidelines and standards that are in place for the use or application of causal ML in the healthcare sector. So in conclusion, and some of the key things that I've mentioned is, first and foremost, is embracing causal ML helps us to harness causal insights, and this helps for improved decision making, patient outcomes, and help improve public health strategies. Another thing is continuous learning and adaptation. We know that there are a lot of advances or advancements in computational techniques. So integrating causal ML into health, we need continuous learning and adaptation to maximize this. And then the last one is empowering healthcare transformation. I just want to tie that back again to the goal of precision medicine, which is to effect change, which is to have actionable decisions. And then with causal machine learning, we can shift our focus from just looking at patterns to looking at cause and effect relationships. Thank you.
Great, thanks, Mo. Actually, although we hadn't planned it, this for me is the perfect one to end this session with, because causality has been, for as long as I can remember in AI, one of the things that we found most difficult to deal with, hugely challenging technically, and here it is back again, but in a more positive way inside healthcare. So that's quite useful. So any questions here? We've got, sorry, I've got one from Sudipta Chowdhury. He says, my question is related to applications of causal ML in health systems in continuum of care for patients with multiple chronic diseases. Will causal ML help in identifying and improving patient journeys across and in between different care points, even in the case when multiple confounding factors and uncertainties are both known and unknown? What could be the benefits and limitations to this? That's quite a complicated question, but maybe you can pick through it.
Okay, so I'll just read it. So question is related to applications of causal ML in health systems and the continuum of care for patients with multiple chronic diseases. the causal ML help to identify and improve patient journeys across in between different care points, even in the case of multiple confounding factors. Okay, so to answer this question, let me pick it again. Just a second. Okay, so to answer this question, so for multiple confounding, for example, I would say that what causal ML does, I would speak in terms of causal discovery. What causal ML does or can help us with is we can identify these confounding variables, and then we can isolate them to be able to now look at the actual causes of certain diseases. So yeah, that's how best I can answer that.
Yeah, good. So yeah, I mean, this is really a complicated question because we're not really. Actually, this is a question to you, Mo, I suppose, which is, I mean, causality is like one of the big underlying issues in cognitive science. Just understanding that. So nobody's expecting you or anybody else to solve all of the problems of causality. That doesn't. Sounds too hard. Yeah, maybe somebody does, but it sounds very hard. So a lot of these things will come down to being very targeted. So I suppose maybe that's part of the question is what might be good targets where you really want to worry about that. I think part of that was in your talk, actually, where you tried to talk a little bit about areas. I don't know, want you to say anything more about sort of practically where people are thinking about applying these sorts of things? Or they may not be known yet. It's quite an open area.
Yeah. Oh, sorry, I didn't get the question in that.
I guess well, I'm reinterpreting the question. I suppose it's more to do where in practice is a good area to apply this sort of technique. I suppose is a kind of blunt version of that question.
Oh, okay. Okay, so some specific areas where we can apply this is in some diseases like let's say diabetes, for example, or cardiovascular diseases. So you know, areas where we have used machine learning techniques, but instead of just looking at the patterns or looking at associations, we're able to actually look at specific causes of those diseases.
Good. Any more questions? You can put up your hand, or you can put them in the chat.
Sorry, I would like.
There's somebody. Hello.
Yeah, sorry, I would like to ask a question about causal ML because today, incidentally, I was in a training course about causal inference, and they only use regression-based methods. So, what would machine learning add to already established, well-established, actually, causal inference methods based on just regression? Would machine learning add to the complexity, or would it add new methods to that? Thank you.
Okay, so what that would do is it would actually add a level of complexity, or how let me see how best I can explain that. So for causal machine learning, we use the double machine learning method, which actually is, so we're able to use some of the traditional machine learning methods that are already being used. However, we just put in the causal inference methods into that to be able to look at cause and effect relationships.
Good. Okay.
Yes, it's a follow-up question.
Yeah,
can you imagine using language models like GPT models with causal inference? Is that even doable at the moment?
To be honest, I'm not sure about that.
Anybody else want to give some thought? When people who work on LLMs want to say something about that? I would be surprised if people hadn't explored that a bit, possibly not in this group, but I guess we'll have to leave that one unanswered. Nobody, no, oh, was Hong Han flickered into
Yeah.
Were you going to say something, Hong Han?
Yeah, it's about these last point of using GPT
Yeah,
model.
go
I
on.
think that definitely some people are studying that. So based on my a little bit experience, I think people trying to, because the good thing of these generative models is they somehow can communicate with people, right? They can have conversation with them. So people are trying to say, can you just explain why you make the decision like this? Sometimes they make explanation. People use some kind of chain of thought to say why this model come up with this decision. They give you a chain of thoughts. But I have to say, it's just a little bit ad hoc. There's no kind of formal mechanism behind this because a lot of times these models just general rubbish in many situations. So it's a potential. What I'm trying to say. It's a potential, but it's far away from make the really reliable in that. But potentially possible in the future, I guess. Especially about the morning's talk. One talk is talking about break down the whole big question to subtasks. And for each task, you have kind of using formalized approach so that you have a more formalized way to answer the question. Kind of that might be an interesting idea to do this actually.
And here's another question from Prashanta Gayer. Says, do you have any experience on incorporating ML algorithms in establishing causal relationships in cross-sectional data, particularly survey data? You done any of that?
No. So actually, causal ML is more some sort of personal interest, which I'm still doing more research about, and hoping to gain more experience actually applying this. So no.
Yeah, and there's a follow-up from Bashanta saying using within a DAG, which I assume means directed acyclic graph.
Exactly, graph.
But the answer to that is no. Also,
No.
so there would be obvious connections into lots of other work that have used DAGs, I suppose. Good. Any more questions from anybody? Is it conceivable that I might actually have run one of these things perfectly to time? That's would be a first. And I don't think anybody wants to throw anything in. So let me just sum up a little bit, if I may, at the end. So firstly, just to thank all the speakers. I really did genuinely think there's a really good series of talks, all of them in their different ways. And thanks, Serena and Rebecca, especially Serena, for keeping us in a state of serene calm as we manage all of this. It is really difficult to organize behind the scenes, despite technology works well, but as you know, it all has to be organized behind the scenes before it works well. So thank you. And I think it is important to do something like this. I hope you agree by the end of the day, and people watching in YouTube, I hope you also agree, because I think what we've done is we've covered really quite a broad space if you look at it. So AI is on the move. I hope people got a sense of that. Exascale definitely on the move. You'll have got a sense of that as well. Quantum computation, disruptive as ever, hard to pin down, but definitely on the move. And then we've been looking at various people who are doing great work, working with a lot of these techniques and trying to understand what they might mean in healthcare. So this is the struggle that we all have. So all of this is like a little snapshot of how things work. And I hope that's valuable to you, either directly or just in a thought-provoking way. I think it's very important. And of course, you might feel a little bit unsatisfied that we didn't give you the answers to many problems. And the reason why is because nobody knows. It's a bit like, reminds me a little bit of one of the advantages of being old is you can remember old things. I remember Bill Gates, people talking about the web when we were very unsure whether the web was a good idea. I'm old enough to remember groups of academics standing around talking about the World Wide Web and saying this World Wide Web's never going to work because all the the links will go stale. It's never going to work. And I remember Bill Gates saying something like, if I remember correctly, it's very, very difficult to know how to bet on the web, but the only bad bet to make is against the web. And it's kind of like that. We don't know how any of the things we've talked about will really play out, but it'd be a very bad idea, I think, to bet against them, at least some of them. So I'll leave you with that thought, unless anybody else has any further thoughts. All I've left to do is to thank you very much for your participation, which has been very helpful. Enjoy the rest of in Scotland, as you can see. Very sunny afternoon, and enjoy your tea. Thanks. Bye.
Thank you, Dave.